This is a general English question. We have been given four sentences and we need to determine among them which is the most suitable sentence with respect to grammar and usage. Now looking at the first two options, the sentences are almost similar. The only difference lies is over here. In option A it is does not over here, while in option B these two different words does not have been clubbed into one single word doesn't. Looking at the entire sentence, I will not leave the place until the minister doesn't meet me. Now, this sentence does not actually make the sense which it is intending to do because we have a negation embedded over them two times, once over here and once over here. So these two negations will actually cancel each other and the sentence will not serve its purpose. So the correct option will be among C and D. Looking at option C, I will not leave the place until the minister meet me. So yes, it is trying to convey the correct meaning that I want to meet the minister and I will not leave before I meet him. So the meaning being conveyed is correct. But grammatically, there is one small mistake in the sentence because this minister is a singular noun. So the verb which will go along with it must be a plural verb. And this meet is a singular verb. So we need to use the plural form of meet and that will be meets. So the correct option is D. This sentence is grammatically correct. I will not leave the place until the minister meets me. So yes, this is the correct option. We'll go with option D. This is a general English sentence. We have been given a description and we need to identify which of these following words fit that description correctly. A rewording of something written or spoken is a dash. Let us look at the options. The first one, paraphrase. That is basically, let us say, some author has written some literary work, a poem or article, anything, and we are trying to express it in our own words to somebody else. So we have actually reworded that and it was already written or spoken by somebody. So that's not our own creation, but somebody else's. And we are simply recreating that. So that is what is called a paraphrase. So this word is suiting the given description. Let us also see the other options if we have a better choice. This is paradox, and as we know, paradox is something contradictory or impossible fact being trying to be conveyed. For example, there might be something illogical or opposite meanings being applied through the same sentence, such as let's say it's a paradox that some countries have abundant food while in other countries people are starving. So same sentence is conveying two different ideas, so that can be called to be a paradox. Now looking at option C, paradigm, it's just like a set of rules or principles or a way in which particular things are done, just as we have programming paradigms, which means a set of rules and conventions that we follow. So that is not suitable in this case. And option B, paraffin, as we all know, it is a kind of wax that is used for making candles and other things. So definitely it's not correct. So the correct option for this will be paraphrase, which is a rewording of something written or spoken. So that appropriately fits the sentence. So we'll go with option A. This is a general English question. A statement quoted by Archimedes has been put over here, which is give me a lever long enough and a fulcrum on which to place it, and I will move the world. Now, as we know, this experiment forming a simple machine which we studied in the school days, a setup such as this, there is a lever and a fulcrum, and some load is put on one side and then it is moved with another weight, that kind of thing. So what he is trying to say that if he gets an arrangement big enough, then he can move the world with it. Now, as we can see, this is an exaggerative type of sentence. It does not make sense in the real world. So we need to identify what type of sentence it is from these given options. First one is saying figurative, which means something which is not in the literal sense. It is trying to convey some another meaning. Now, by this sentence, Archimedes is trying to convey some other fact. He's not literally saying that he will move the world. He's just trying to say that he has that potential that he can bring about some change in the ideologies or method which people usually follow. He will change their mindset. He's not actually going to place Earth over there and going to displace it. So this kind of sentence can be said to be figurative, which is not in the literal sense or that is deviating from the real world facts, but just simply an exaggeration. So this is the correct option for this particular case. Let us also have a look at other options. This collateral term is not generally used in the English grammar. It is more associated in the with finances and loan, etc. kind of thing. In that context, this word is seen to be used, such as when you take some loan, you have to put something in exchange of that, which means if you're not able to repay that loan, then you will give away that thing to them in return, that kind of. So this collateral is not making sense over here. This literal means whatever is being conveyed will be literally done, but this sentence does not make sense in the real world, so again this will be discarded. And the last one is figurine. Now again, this is a noun which is generally used for some statue or any small ornamental decoration kind of thing, so again that is not suitable over here. So the correct option will be A, figurative. This is a coding decoding kind of question. We have been given three words and their encodings, which are RELF, TAGA, RELF, TAGA, corresponding to carefree. The next word is OTAGA, OTAGA, corresponding to careful. And the last FER, TAGA, corresponding to careless. Now, using these three encodings, we need to determine what will be the possible encoding for the word aftercare. Now, as we can see, in all these three words, the common thing is this prefix care. And among these three words, there is a common suffix TAGA, TAGA. So we can say that this care corresponds to TAGA, but here it is a suffix and here it is becoming a prefix. So in our word, since we want care to be a suffix, over here this TAGA should become a prefix. So we will have some word beginning with TAGA. And what will be the suffix for this word? Now let us understand that with this. Here this RELF is corresponding to free, O is corresponding to full, and this FER is corresponding to less. Alright, now depending upon these facts, let us look at the option. We want something beginning with TAGA, so that is only there in options B and C. But looking at option B, it is having a suffix FER, and we just saw that this FER fair corresponds to less. So this will actually mean after, instead of aftercare, this will become less care. So that is incorrect. So the correct option must be TAGA Zen, because this TAGA corresponds to care, which will be a suffix, and this Zen will correspond to some prefix, which in this case has to be after, as there is no other option. So the correct option would be C, TAGA Zen. This is a logical reasoning type of question. It is said that we are forming a cube using 64 small cubic blocks, and then from the resulting cube we are removing one cubic block from each of its corners. We need to determine the surface area of the resulting shape. Now, as we know, if we are building a cube using 64 small cubic blocks, then that will become a 4 cross 4 cross 4 cube, because this volume 4 cross 4 cross 4 will lead to 64 cubes in total. So each of its sides will have 4 into 4, which is 16 cubes. So this is how the figure will look like. This will be the resulting 4 cross 4 cube, something like this. And now the surface area of this particular shape will be 6 times of area of its side, because it has 6 sides and all of them are having the same area, and the area of every side is 4 cross 4. So this is the surface area, and that translates to 16 times 6, which is 96. Now they are saying that it has 8 corners, and from all of its corners we are removing one cube each. So let us say this is the corner we are considering, so this particular cube will be removed, and this will happen for all the 8 corners. Now as we can see, this particular yellow area, it is covering 3 sides in total, which means when we remove this particular cube, then 1, 2 and 3, these 3 unit area will be removed by this particular smaller cube. But when we take this particular small cube out, then it will expose another 3 surfaces. Simply the shape is currently concave, but when we remove this off, then the shape will be something like this. It will be kind of a distorted cube. But another three sides will be exposed when these three are removed. So basically, in turn, no reduction in surface area will take place, because if we remove from all the corners, then same number of newer surfaces will emerge out. So there will be no loss of any surface area, and the resulting area would still be 96, because here if we are removing 3, then we are also adding 3, and the same thing happens at all the 8 corners. So there is no reduction and the answer will still be 96. So the correct answer is D. This is a data interpretation type of question. We have been given the sales data of a company for the 4 quarters. It is a shaving set company selling 4 different type of razors, which is elegance, smooth, soft, and executive. Their selling price per piece has also been given. So we need to determine the total revenue generated for the company by one of these brands, the one which is generating the highest revenue for the given financial year. So basically we don't need the data separately for all these quarters. We shall sum the entire thing for the whole year and then calculate the revenue. So summing these values up, for the Elegance brand, we get the total sales as 102510. For Smooth, we get 80059. For the Soft, we get the sum 72186. And for Executive, we get the sum as 39284. Now, these are the total sales of these brands in the given year. Now, in order to get the revenue generated by them, we shall multiply this value with their selling price. So, for Elegance, we shall multiply by 48. The result will be 4920480. For Smooth, it shall be multiplied by 63. Result will be 5043717. For Soft, we will multiply by 78. Result will be 5630508. And for the Executive, we shall multiply by 173, which is the highest among them all, and that will give the result 6796132. Now, as we can see, among these 4 values, the one which is maximum is the last one for the Executive brand. So this is the brand that is generating the highest revenue for this company in the given financial year. Hence the correct answer will be option B, Executive. This is a reasoning type of question. We have been given a statement, and based upon that we need to determine which of these following conclusions can be inferred from that. It is saying that Indian currency notes show the denomination indicated in at least 17 languages. If this is not an indication of the nature's diversity, then nothing else is. Now let us look at the options. India is a country of exactly 17 languages. Now this fact may or may not be correct, but it is definitely not being implied from the given statement. It is simply stating that the denomination is indicated in at least 17 languages. It is not talking about how many languages are existing in the country. So this sentence is incorrect. It is not being implied from the given statement. Second one is saying that linguistic pluralism is the only indicator of the nation's diversity. The statement is saying that if this linguistic pluralism, this particular thing has been called to be the linguistic pluralism, it is saying that if this is not an indication, then nothing else is. Which means that this is one of the indications. It is not saying that this is the only indication. It is simply one of the indications of the nation's diversity. So if this is not true, then nothing else will be true. So this statement is also incorrect because it is not only but one of the most prominent ones. Hence incorrect. Now looking at the next option C, Indian currency notes have a sufficient space for all the Indian languages. Now again, this fact may be true, but it is not being implied from this sentence. Yes, it is accommodating 17 languages, but the main fact being conveyed is about the indications of nation's diversity. So again, this statement will not be considered. The last one is saying that linguistic pluralism is a strong evidence of India's diversity. Yes, to some extent, this statement can be drawn as an inference from this, because it is talking about linguistic pluralism and also saying that it is an indication of nation's diversity, and if this is not true, then nothing else will be true, which means yes, this is one of the most prominent and strong evidence of India's diversity. So we will go with option D because it's the most correct appropriate sentence which is being drawn from the given statement. So option D is the right answer. This is a logical reasoning type of question. We have been given 4 players, P, Q, R and S, who are the poker players, and 4 statements about them have been given. Based upon that, we need to determine which of these conclusions hold true. First one is saying that P always beats Q. Let us denote that with this notation. P always beats Q. R always beats S. Next is S loses to P only sometimes, which means P only sometimes beats S. So let us denote it this way. Last is R always loses to Q, which means Q always beats R. So these are the 4 statements we got. And now let us look at the conclusions. P is likely to beat all the 3 other players. P can beat Q, alright, but coming to this, P is beating S only sometimes. Other times, P is getting beaten by S. Hence, it is not likely to beat all the 3 other players. And also, we don't know anything about how P and R play together. But it is given that P beats Q, Q beats R. So definitely P might also be beating R, but that does not get directly implied over here, and we cannot say that the conclusion is being drawn. So we will reject this statement. Next is saying S is the absolute worst player in the set. Again, this particular reasoning is saying that P only sometimes beats S, which means other times S might be beating P. This is also being implied by the same statement. Both are logically same. So we cannot say that S is the absolute worst player because sometimes it can beat P as well. Hence, we can say that none of these 2 conclusions are being drawn. Neither 1 or nor 2 are correct. So we shall go with option D. Question. We have been given a polynomial 2x raised to 7 plus 3x minus 5. We need to determine which of these 4 will be the factor of this particular polynomial. Now here we don't actually need to apply actual mathematics or division or anything. We can simply look at the options and say that if this had to be the factor of this polynomial, then x cube equal to 8 must satisfy this particular equation. But let us try to do that. If x cube is equal to 8, then x will be 2. Let us see if it satisfies this polynomial equal to 0. Putting x equal to 2, we shall get 2 times 2 raised to 7, which means 2 raised to 8 plus 3 into 2 minus 5. This is definitely non-zero. Hence, that's incorrect. Looking at option B, x equal to 1. If this had to be the factor of this equation, then x equal to 1 should satisfy it. Let us try substituting x equal to 1. We shall get 2 times 1 raised to 7, which means 2 plus 3 minus 5. So yes, this is satisfying the equation, which means this will be the factor of the given polynomial. Let us also check other options. 2x minus 5. If this had to be the factor, then we shall substitute x equal to 5 by 2 and that must satisfy the equation. So 2 times 5 by 2 raised to 7 plus 3 times 5 by 2 minus 5. This will definitely not satisfy. So again, that's incorrect. And x plus 1 means x equal to minus 1 must be the root of this polynomial. So substituting minus 1, we shall get minus 2, minus 3, minus 5. Again, that is non-zero. So the only factor of this given polynomial will be option B, x minus 1. So that is the correct answer. This is a mathematical reasoning type of question. We have been given a process which takes a number of cycles to failure and that decreases exponentially with an increase in load. So this can be mapped with an exponential function such as number of cycles equal to, let's say, some a times e raised to minus bx, where x is the load and we have taken a and b as the constants. This is negative because it is decreasing exponentially. So given the first value, with a load of 80 units, it is taking 100 cycles. So we can write first equation as 100 cycles equal to a times e raised to minus b into 80. So we can say minus 80b. This is the first equation. Next, it is saying that when the load is halved, which means this x value is reduced to 40, then it takes 10,000 cycles. So we can say 10,000 equal to a times e raised to minus 40b. This is the second equation, and they are asking us for the number of load factor required for 5000 cycles. So that will be 5000 equal to a times e raised to minus b into x, and we need to find the value of this x. So using these two equations, we can find out the values of a and b and then put them in this particular equation to find the value of x over here. So let us divide these two equations together and we shall get 10,000 upon 100 equal to a times e raised to minus 40b, a times e raised to minus 80b. Dividing them, we shall get 100 equal to e raised to minus 80b will come upside, that will become 80b minus 40b equal to 40b. So from here we can take ln on both sides, which is log to the base e, that will give us ln 100 equal to 40b. ln e will be 1. So from here we get the value of b as ln 100 upon 40. Now we shall put this value of b in equation 1 to get the value of a. That will give us 100 equal to a times e raised to minus 80 times ln 100 upon 40. That will be a times e raised to minus 2 ln 100. So now we can write this thing as, let us take ln on both sides. So ln 100 equal to ln a minus 2 times ln 100, because again ln e will be 1. So we can write ln a equal to 3 times ln 100. So from here we can say that ln a equal to, this 3 can be raised there, so this will be 100 cube. So a equal to 100 cube or 10 to the power 6. So now we got both the values of a as well as b. So let us substitute them here and get the value of x for this equation. This will become 5000 equal to 10 power 6 into e raised to minus ln 100 upon 40 x. We need to find the value of this x. So this will become 5000 upon 10 to the power 6 equal to e raised to minus ln 100 upon 40 x. Let us take ln on both sides and this thing becomes 1 upon, this 3 gets cancelled, so this is 1 by 200, and we can make this as ln of 1 by 200, which means minus of ln 200 equal to minus of ln 100 by 40 into x. Minus gets cancelled and what we get is 40 ln 200 upon ln 100 as the value of x. So this actually becomes 40 times ln of 200 upon ln of 100, which can be said as 40 log 200 to the base 100. Now this value you can calculate using a calculator, and that turns out to be 40 times of 1.15 approximately, and this value becomes 46.02, and that matches with our option B, so that will be given as the answer. When the load is 46.02 units, then the failure will take place in 5000 cycles. So our answer will be B, 46.02.
Let P, Q, R, S represent the following propositions. P states that X belongs to the set 8, 9, 10, 11, 12. Q, X is a composite number. R, X is a perfect square. S, X is a prime number. The integer X greater than or equal to Q which satisfies the following expression is dash. So this is a question from engineering maths from the section propositional logic. So here they have given us 4 statements, each of which assigns a value to X according to the rules given there, and they are asking for which value of X will this statement become true. So let's try to simplify this one. P implies Q, we can rewrite it as negation of P or Q. So I will write it as negation of P or Q and negation of R or negation of S, and there is a negation outside, that means complement, so I just write it as complement here outside. Now if you look, it's of the form a and b the whole complement. A and b the whole complement is a complement or b complement according to De Morgan's law. So this I can rewrite it as negation of p or q the whole complement, or negation of r or negation of s the whole complement. Again, a or b the whole complement is a complement, b complement. So negation of p or q the whole complement, I can rewrite it as p q complement, and negation of r or negation of s the whole complement, I can rewrite it as rs. So the entire statement becomes p q complement or rs, which means that p should be true and q should be false, or r should be true and s should be true in order for this statement to become true. Now let's take a look at the statements given. The propositions. P says that x belongs to 8, 9, 10, 11, 12. So let's write down the values of x here in P. In P, the value of x is 8, 9, 10, 11, 12. Now here it says that it should be P and Q complement. So instead of Q, I will write Q complement here. What's the proposition Q? It says that x is a composite number. So the complement of that will say that x is a prime number. So I will write down the values of Q when it is prime. Q complement will become 2, 3, 5, 7, 11, 13, 17, etc. These are the prime numbers greater or equal to 2. Okay. Now I will write down R. X is a perfect square and x is greater or equal to 2. Meaning the value of x will be 4, which is 2 square, 9, which is 3 square, 16, which is 4 square, etc. So R will be 4, 9, 16, etc. going to the right. And S says that x is a prime number. Again, it's the same thing as Q complement, that is 2, 3, 5, 7, 11, 13, 17, etc. Now let's try to satisfy this one. Let's try to satisfy this part, RS, which says that R and S should be true. Now R says that x is a perfect square and S says that x is a prime number. Now x is greater or equal to 2. There is no number which is a perfect square and is also a prime number. If x is a prime number, it means that it doesn't have any factor other than x and 1 itself. But for x to be a perfect square, it should have at least one factor, that is the root of x. So these two statements cannot go together. So this statement we can't ever satisfy RS together. Even if you look at the numbers here, there is nowhere where the numbers will overlap. So this part we can ignore. RS will never be true. Now let's look at PQ complement. P says that it belongs to 8, 9, 10, 11, 12, and Q complement, it says that x is a prime number, which is 2, 3, 5, 7, 11, 13, etc. Now, which P and Q complement both are true, it means that the number belongs to 8, 9, 10, 11, 12 and it is a prime number. Now the only number that belongs to 8, 9, 10, 11, 12, that's a prime number is 11. So you can see here. So when x is 11, P is true and Q is false, meaning this statement as a whole, it will become true. So the smallest value of x which satisfies this is x equal to 11, and it's the only value which will satisfy this. Let an be the number of n-bit strings that do not contain two consecutive ones. Which one of the following is the recurrence relation for an? And 4 options have been given here. So this is a question from recurrence relations coming from engineering mathematics. Here an is the number of strings that do not contain two consecutive ones. The number of n-bit strings that do not contain two consecutive ones. So A1 will mean the number of 1-bit strings that do not contain two consecutive ones. A2 will mean the number of 2-bit strings that do not contain two consecutive ones, etc. So let's try to find out the value of A1, A2, A3, etc. and then try to plug it into each of the equations here and see which one works out for us. So let's try to find out A1, the number of 1-bit strings that do not contain two consecutive ones. Now in a 1-bit string, there is no way two consecutive ones can appear since there is only one digit. So there are two strings, that is 0 and 1. So A1's value will be 2. Now A2 are 2-bit strings. Okay, so we can take 0, 0, 0, 1, 1, 0, but we can't take 1, 1. If we take 1, 1, then it will have two consecutive ones. So that is not correct. Meaning A2's value is 3. Let's take A3. We can take 0, 0, 0, 0, 0, 1, 0, 1, 0. We can't take 0, 1, 1 because it will have two consecutive ones. Let's take 1, 0, 0, 1, 0, 1. That's fine. 1, 1, 0 and 1, 1, 1 will again have two consecutive ones. So those also we can't take. So A3 is only these many strings. So A3 is 5. Now let's try to plug these values into the equation and check. We know A3 will be equal to, in all of these expression it's given in terms of a n minus 1 and a n minus 2. So when n is 3, a n minus 1 is 2 and a n minus 2 is 1. So we need to write A3 in some form of A2 plus A1. The options are, here I can put 1, here I can put 2, here I can put 1, here I can put 1, here I can put 2, here and here I can put 2. So let's try all those values. We know A3's value is 5, that's equal to A2's value is 3 plus A1's value is 2. Now if you see clearly, 5 equal to 3 plus 2, that's directly we are getting 5 when we add 3 plus 2. So the coefficient of this will be 1 and 1. 5 is 1 into 3 plus 1 into 2. Now if you look at the options, only option B has the coefficient as 1 and 1 for n minus 1 and n minus 2. So this is the answer. For A, B and C there is some coefficient which is not equal to 1 associated with a n minus 1 and a n minus 2. That will only increase the total value greater than 5 as evident from this here. So the answer is option B. Limit x tends to 4 sin x minus 4 by x minus 4. This is a question from engineering mathematics regarding limits and derivatives. So there are two ways to solve this question. One is that if you learn calculus, limits and derivatives, you will see that limit t tend to 0 sin t by t will be equal to 1. This is a well-known formula. Now we can just apply the formula here. If we substitute t equal to x minus 4, then I can rewrite it as limit t tend to 0 sin t by t, which will be equal to 1 from our formula here. Now that's the easy way of solving it. There is also one more way. Even if you don't know this, you can solve this easily. If you just substitute x equal to 4 in the equation, we will see the equation will change to limit x tends to 4 sin of 4 minus 4, that is 0 by 0. Sin 0 is 0. So this entire expression will be 0 by 0 form. Now if you know if an expression is in 0 by 0 or infinity by infinity form, we can apply the L'Hospital's rule. Now L'Hospital's rule states that limit x tend to c, f of x by g of x will be equal to limit x tends to t, f dash x by g dash x, if f of x by g of x was in 0 by 0 or infinity by infinity form. Now applying that here, I will take the derivative of numerator and denominator. Now numerator is sin x minus 4, its derivative is cos x minus 4. Denominator is x minus 4, whose derivative is 1 only. So I will rewrite it as limit x tends to 4 cos x minus 4 by 1. I will substitute x equal to 4 in this, which will become cos 0 minus 0 by 1, which will be equal to cos 0, which is 1. 1 is the answer to this question. A probability density function on the interval a to 1 is given by 1 by x square, and outside the interval the value of the function is 0. The value of a is dash. This is a question from engineering mathematics regarding probability density functions. Now here the density function is defined as 1 by x square. So let's try to draw the graph for 1 by x square. The graph of 1 by x square will look like this. At 0 it will be 1 by 0, which will go to infinity. At 1 it will be 1 by 1, which will be equal to 1. And as x increases, the value keeps on decreasing. Similarly in the negative part also it will be just the mirror image of this. Okay. And they are saying that our probability density function is defined only in the open interval a to 1. Meaning in the interval a to 1, let us imagine a is at this point. It can be anywhere on this axis. Let's say a is here. So from a to 1, the value of our function would be 1 by x square, which is given by this line. And outside the interval, the value of the function would be 0, that is defined here. So our probability density function will look like this. From a to 1, it will be the value of 1 by x square, and outside a to 1, it will be 0. So this is how our probability density function looks like. Now the property of a probability density function is that the total probability should be equal to 1, which means the area of the graph under this line should be equal to 1. Now the area of the graph is integral a to 1, 1 by x square, that is integrating from here to here. So which means integral a to 1, 1 by x square should be equal to 1. Now integral of 1 by x square is minus 1 by x, which means that minus 1 by x from 1 to a should be equal to 0. This I will substitute 1 here. When I substitute 1 here, I will get minus 1. When I substitute a, I will get minus 1 by x. So minus 1 minus minus 1 by x is minus 1 plus 1 by a, which is equal to 1. Now I can rewrite it as 1 by a equals 2 and a equals to 1 by 2, which means that this point a is nothing but 0.5. So the question was to find a, the value of a is 0.5. Two eigenvalues of a 3 by 3 real matrix P are 2 plus root of minus 1 and 3. The determinant of P is dash. So this is a question from linear algebra. It's a very easy question. It's given that two eigenvalues of a 3 by 3 real matrix P are 2 plus root of minus 1 and 3. A 3 by 3 real matrix will have 3 eigenvalues. Okay. And given the eigenvalues are 3 and 2 plus I is root of minus 1. Okay. So if one eigenvalue is a complex number, then another one would be the conjugate of this complex number. How we got this is that we got eigenvalues. If there are 3 eigenvalues, that's a solution of a polynomial equation of degree 3, and on solving that, if one of the roots is a complex number, then its conjugate will also be a complex number. So which means that if 3 and 2 plus I are eigenvalues, if 2 plus I is an eigenvalue, then 2 minus I is also an eigenvalue of the matrix, meaning 2 minus I is the third eigenvalue here. Also, we know the determinant of a matrix will be equal to the product of its eigenvalues, which means that the determinant of P will be 3 into 2 plus I into 2 minus I. These are the eigenvalues which we got, which will be 3 into, solving this, we get 4 minus I square. Now I square is minus 1, 4 minus minus 1 is 5. So the final answer would be 3 into 5 equal to 15. 15 is the answer. Consider the Boolean operator with the following properties: x hash 0 equal to x, x hash 1 equal to x complement, x hash x equal to 0 and x hash x complement equal to 1. Then x hash y is equivalent to, we have been given 4 options here. So this is a question from Boolean algebra. We just need to find out what this operator hash does. So let's draw the truth table for x and y and all the possible states. That is, write down that is 0 0 0 1 1 0 and 1 1. Now let us see 0 hash 0. Now this I will take as x hash 0, which will be x only. So x hash 0 will be x, here x is 0. Similarly, this is x hash 1. X hash 1's value was x complement, that is 0's complement, that is 1. This is x hash 0. X hash 0 is again x only, so I will write 1 here. X hash 1 is x complement, which is given here, x hash 1, which is x complement, that is 1's complement, that is 0. So we only needed these two statements to draw the truth table. Now we will verify the same thing using these two statements as well. This states that x hash x equal to 0. Now that is in this case, which is 0 hash 0 and 1 hash 1. There the value should be x. So 0 hash 0 would be 0, it's given here. 1 hash 1 also should be 0, given here. Similarly, x hash x complement was 1. That is 0 hash 1 and 1 hash 0, which is 1. So we only needed these two to draw the truth table, but on verifying with these two as well, we are getting the same thing. So x hash y is 1 for these two parts. Now this will be x complement y and this will be x y complement. So the value of x hash y will be x complement y plus x y complement. That is given in option A. Option A is the right answer here. The 16-bit 2's complement representation of an integer is 1111, 1111, 1111, 0101. Its decimal representation is dash. So this is a question from number systems in digital logic design. So in 2's complement representation, if the most significant bit is 1, means it is a negative number, and if the most significant bit is 0, it means that it is a positive number. So let's take a look here. To get 2's complement of a number, we complement all the digits and add 1. So this is a negative number, so let's take 2's complement of it and see what we get. So when we take a 2's complement of it, we'll get the corresponding positive number of this one. So I'm taking 2's complement. For that I'm complementing all the digits initially, and then after that I'm adding 1. So this number becomes 0 0 0 0 0 0 0 0 0 0 0 0 1 0 1 0 plus 1 will be 1 0 1 1 and a number of zeros. Now this number is nothing but 11 in base 10. Okay, so this is the corresponding positive number of this negative number. So this number was negative, that is just negative of this one, that is minus 11. So minus 11 is the answer to this question. There was an easier way to do this. In the 2's complement representation, if it's a negative number, all the digit ones after the sign bit, we can just eliminate it to get the same number. That is, even if I removed all the ones from this number, I would have got 1 0 1 0 1. This would be the same number as this one. The only difference is this is a 5-bit representation, whereas this is a 16-bit representation. Even if I take this number, the value would be the same. So for this number, I will try to take the 2's complement, that is 0 1 0 1 0 plus 1 would be 1 0 1 1, same as this one. So keep that in mind. Yeah. We want to design a synchronous counter that counts the sequence 0 1 0 2 0 3 and then repeats. The minimum number of JK flip-flops required to implement this counter is dash. So this is a question from sequential circuits in digital logic design. They are asking us to design a counter that will be counting this sequence 0 1 0 2 0 3, and they are asking what's the minimum number of JK flip-flops needed to do that. So let's take a look at these numbers. So in first look, you will see that there are only 4 states here, that is 0 1 2 3, and then it is moving between 0 1 2 and 3 in this order given here. But on a closer look, you will see that it is not just 4 states, because from this 0 I am going to 1, and from this 0 I am going to 2, and from this 0 I am going to 3. So even though in these states it is displaying 0, these 3 states are not the same state, because if these were same state, from one state I can only go to another unique state. So if there was only one state for 0, it can either go to 1 or 2 or 3. It can't go to 1 in one point and 2 in another point and 3 in another point. So we need 3 different states to print 0. Okay, so if there were only 4 states, we could have printed it like this: 0 0 0 1 1 0 1 1. Now this would have counted 0 1 2 3, but then we need 3 unique states for 0 itself. So if we add one more bit to this 0, we can write it as 0 0 0 or 1 0 0. And if we take the least significant, the 2 least significant bits and display it, you will see that it will be displaying 0 in both the cases. But these two are 2 different states, because on the left side there is 0 and 1. So what I have effectively done here is, by adding one more bit to the 0, I can make it 2 different states. But we need 3 different states, so we need to add one more bit. So let us add one more bit. That means we are adding 2 bits in total. Now I can have 4 different states for 0. And consider these states: 0 0 0 0, 0 0 0 1, 0 1 0 0, 0 0 1 0, 1 0 0 0, 1 0 1 1. So these 3 are zeros, and I have added 2 bits to the left side to differentiate between these zeros, which is 0 0 will be 0 1, the first 0, and for 0 1 and 0 0 it will be the second 0, 1 0 and 0 0 it will be the third 0. And for 1 2 and 3 we can just keep 0 0 in that bits. We don't need these 2 bits to represent 1 2 and 3. We already had 0 1 1 0 and 1 1. So if you look at this flip-flop, if you look at this counter, and if you take the least 2 significant bits, the 2 least significant bits, it is displaying 0 1 0 1 0 1. So this counter is effectively displaying the numbers. It is counting 0 1 0 2 0 3 etc. in a loop. So this is the way to design the counter to count the sequence. Now if you look here, there are 4 bits in this counter, right? Even though we are displaying only 2 bits, there are totally 4 bits in the counter, which means for a 4-bit counter we will need 4 flip-flops. So 4 is the answer. But in this question, if you see, even though we designed here using 4 bits, 4 JK flip-flops, there are only 6 different states here, right? We need 3 states for 0, and then we need 1 2 and 3. So in total there are only 6 unique states. Now 6 unique states we can even represent using 3 bits as well. So let us say I assign 0 0 0 to the first 0, 0 0 1 will be 1, 0 1 0 will be 2, 0 1 1 will be 3. Let us assign 1 0 0, let's define 1 0 0 will be our second 0, and 1 0 1 will be our third 0. Now we can easily design a counter to count between these numbers. This is a 3-bit number, right? So this we can easily design using 3 flip-flops. Using 3 flip-flops I can design a counter displaying these states. But then I will need additional combinational circuit to show that to convert from 0 0 0 to 0 and to convert from 1 0 0 to 0 and 1 0 1 to 0. 0 0 1 will be 1 only, 0 1 0 will be 2 only, and 0 1 1 will be 3 only. So even though I can design the same sequence counter using 3 flip-flops, that is using only 3 bits, I will need additional combinational circuit to convert from this 0 0 0 to 0 and this 1 0 0 to 0 and 1 0 1 to 0. But in the question it was not given that we could not use any additional combinational circuit, etc. So for this question technically we can design it using 3 flip-flops as well, since we had only 6 different states. Now in this year, so this was the answer expected by the gate authorities this year, but many students challenged this, and even this is also not wrong. So in this year 3 and 4 both were accepted as answer to this question. But the proper way to do this is this way, which I have shown here, and 4 is the answer, like that. A processor can support a maximum memory of 4 GB where the memory is word addressable. A word consists of 2 bytes. The size of the address bus of the processor is at least dash bits. So this is a question from computer organization. This is a very easy question. The only thing to note here is that the memory is word addressable and that a word consists of 2 bytes. So let us see how many words are there in the memory. The size of the memory is given as 4 GB and each word is 2 bytes in size. So the number of words in memory is 4 GB by 2 bytes words, that is equal to 2 GB or 2 power 31 words. Now to address 2 power 31 words we need only 31 bits. So the memory, the processor here needs an address bus of size 31 bits only. 31 is the answer. A queue is implemented using an array such that NQ and DQ operations are performed efficiently. Which one of the following statements is correct? N refers to the number of items in the queue. So this is a question from data structures asking us about queues. They are saying that they are implementing a queue using an array here. And it is implemented such that NQ and DQ operations are performed efficiently. It said that both are efficiently performed. Now they are asking what's the time complexity of these operations. Now how to implement a queue using an array is, initially we can have a start pointer and the end pointer. So let's call this front and the ending we'll call it as rear pointer, both pointing to the start of the array. Now there is nothing in the array. Now for NQ what we need to do is we look at the rear pointer and then we increase it by 1, and then the space that we created we will add the element. So let us say we are adding some element here. Now the rear pointer will be pointing to this one. Similarly we can keep on adding like this. So NQ is taking only O1 time here, right? Now the rear pointer is pointing here. Now how will we perform DQ? We have a pointer pointing to the front of the queue, right? So for DQ we'll just remove the first element that is pointed to by the front pointer, and then we'll increase the front pointer by 1. So we can do it like this. For DQing one element we'll just remove this and then we'll point it to front like this. So we can keep on going on like this until the rear pointer will reach the end of the array. Now once that happens, the only thing we need to do is we will be pointing the rear pointer to the start of this array. So just imagine that this array is circular. After this element, consider that this is the element that comes in. So if we implement it in that way, after rear pointer if we need to add, we can increase the rear pointer by 1, meaning we'll go it to 0, and then we can just add there. Similarly for DQing also, the front pointer keep on going in this way, and once it's over it will go to this side. So front and rear pointer implemented in this way, we can easily implement a queue using an array. Both the operations front and rear will take only O1 time. Now this is an implementation of queue, but the only problem with this implementation is that the queue can only grow up to a fixed size, that is the size of the array initialized when we created the array. So the queue can't grow beyond this size. That's the only limitation of this implementation. Implementing NQ and DQ, the time complexity is O1 only. So looking at the options, both operations can be performed in O1. A is the right answer. Consider the following directed graph A, B, C, F, D, E given here. The number of different topological orderings of the vertices of the graph is dash. So this is a question from data structures regarding topological ordering of graph. So what's topological ordering? If we have a graph like this, A is connected to B, A is connected to C, B is connected to D, and C is connected to D. A topological ordering is some ordering of the vertices A, B, C, D, such that since we have an edge here, if there is an edge between two nodes, then the source node should appear before the destination node. So A has an edge with B, meaning that in the ordering, A should appear before B. So a topological ordering of this graph will be some ordering of A, B, C, D such that A appears before B, B appears before C, A appears before C, and C appears before D. So what if we write A, B and D, A should appear first and then B should appear and then D should appear. This order should appear in this way itself. Now where can we put C? The only condition is that C should appear after A because of this edge. Also C should appear before D because of this edge. But between C and B there is no relationship, so C can appear anywhere with respect to B, meaning there are two positions where we can put C, which is immediately after A before B or after B before D. So there are two topological orderings for this sample graph, that is A, C, B, D or A, B, C, D. Now that is topological ordering. Now let's take a look at the question here. So if you see, A should appear before any number here. A appears before B, B appears before C, C appears before F, meaning A appears before all of these nodes in this line. Similarly, A should appear before all of the nodes in this line. So A should be appearing first. Similarly, F should be appearing the last. All the numbers should be coming before F only. So we can write A and F here. If you take B and C, the only relation is that B should appear after A, also C should appear after B, and then C should appear before F. So this is the only ordering in which I can write A, B, C and F. After that I can put D and E in some places. The only rule is that D should appear after A, E should appear after D, and E should appear after F. Meaning that D and E I can only place in the order D, E, such that it appears after A or it appears before F. Meaning D and I can only put in these slots, that is immediately after A before B, or immediately after B before C, or immediately after C before F. Now I have written down all the orderings here. It's just permutation and combination, just assigning D and E in these three slots. Now if you look here, there is only 6 ways of arranging this. You can do it yourself and verify that there is only 6 ways. There is no other way in which I can arrange A, B, C, D, E, F following all the rules specified according to the graph. So the answer to this question is 6. This is a C programming question. They have given us this particular program, and in the program there is a blank line. They are saying that this blank line is a call to the function f. So, and they are asking which one of the following expressions when placed in the blank line above will not result in a type checking error. They have given us these 4 options, each containing one statement, and they are asking which of the options when placed here will cause a call to f without causing any type checking errors. So we will go through the options one by one to find out the answer. First of all, let's look at the program. Here I is an integer, S is a short, and P is a pointer to short. So the data type of I is int, S is short, and P is short star. Okay, now let's look at the options. Option A, it is passing S and star of S. So if you see here, S is a variable of data type short, and we are doing star of S here. Now star of S, this operation can only be done on pointers. We can't do it directly on a variable short S. So this will result in a error here itself. So A is not the right answer. Similarly, if you look at option C also, we are passing star of S here. S is a short. We can't do star of S operation here. It has to be done on a pointer, not a direct short variable. So C is also wrong. Now if you look at option B, it is passing F, is calling FIS, and the return value is being stored into the integer I. But if you look at the function F has a type void. Now it's returning void, and that value is being passed, that value is being saved into I, but I is an integer, so it becomes int equals void. So that's also a type checking error. We can't take the return value of F and store it in I, so this is also wrong. If you look at D, it's calling F with I. Now I is integer, that's the same that we have here, int. And star of P, So P is a pointer to a short variable. Star of P will give us the value inside that. So the value inside this would be 12 only. The data type is short, and it's passing some value of data type short into this function, which is also expecting short only. So this is the correct way of calling it. D is the right answer. The worst case running times of insertion sort, merge sort and quick sort respectively are. 4 options have been given. So this is a straightforward question from algorithms section. They are asking us about the worst case running times of these sorting techniques given here. So in this table I have given the best case, the average case and the worst case running times of insertion sort, merge sort and quick sort. So insertion sort, in best case it will run in O(n) time. This happens when the array is already sorted. Average case and worst case for insertion sort is of n square only. Now the merge sort, in best case, average case or worst case, it runs in n log n time only. Now the quick sort, in best case and average case, takes n log n time, but in the worst case, quick sort takes n square time. So based on this table, they are asking us about worst case. So we can just look at the last row and answer this question directly. So it will take, insertion will take n square, merge sort is n log n, quick sort is n square. So that is given in option D. So D is the correct answer here. I would also recommend one more thing. It's better if you can learn various properties of these sorting algorithms, such as, which I have written here, bubble sort, modified bubble sort, insertion sort, selection sort, merge sort, quick sort, heap sort, counting sort, radix sort, and also the properties such as best case running time, average case running time, worst case running time, space complexity and stability, whether the algorithm is stable or not. So it's better if you can draw a table of all these algorithms and the associated properties and keep it ready with you. Throughout the years, multiple questions have been asked interchangeably regarding these properties of the sorting algorithms, and it's an easy 1 mark or 2 mark for you if you know the answer directly. So you can find out the answer to all this and learn that. So for the question, D is the answer. Let G be a weighted, connected, undirected graph with distinct positive edge weights. If every edge weight is increased by the same value, then which of the following statements is or are true? P, minimum spanning tree of G does not change. Q, shortest path between any pair of vertices does not change. 4 options are given here. So this is a question from data structures topic regarding graphs. Particularly they are asking us about minimum spanning trees and shortest path between any 2 vertices. So we have been given an weighted, connected, undirected graph with distinct positive edge weights. So if you look at this graph, this satisfies all the condition given in the question. It is weighted, each edge has its own weight, it is connected, undirected graph with distinct positive edge weights. All the edge weights are positive and distinct, right? So now consider this as node A and this as node B, okay? Now what is the shortest path between A and B? Here if you see, if you are taking this path, there are 2 paths. I can either take this path or this path. Weight of this path is 3 plus 2 plus 1 is 6 and weight of this path is 7. So clearly 6 is shorter than 7. So the shortest path between A and B is currently this path. That is from A to this node, then this node, then this node, having weight of 6. Now if every edge weight is increased by the same value, then what will be the new edge weights? New edge weights will be, let us say we are increasing value by 1. So let us say this edge weight will be 7 plus 1 8, 3 plus 1 4, 2 plus 1 3, 1 plus 1 is 2. Now the edge weights are 2, 3, 4 and 8. Now which is the shortest path? Here A to B, the path distance is 8. A to B via this one is 2 plus 3 plus 4, that is 4 plus 3, 7 plus 2 is 9. Now 9 is greater than 8. Previously the shortest path was this path, but now the shortest path is this path after we are increasing edge weights. That's because in a shorter path, when we are increasing every edge weight by a constant value, whichever path was having larger number of edges, that has a disadvantage. If a path had 3 edges in it, now when we are increasing every edge weights by 1, the edge weight itself will increase by 3 times we are increasing it by 1. So the edge weight will increase by 3, whereas this path had only 1 edge, so it increased by only plus 1. So in such cases, previously this was the shortest path, but now this is the shortest path. So clearly Q is wrong. Shortest path with any pair of vertices does not change is false. We have proved it with counter example. Now P, minimum spanning tree of G does not change. Is that true? Let us say a graph has 6 edges A, B, C, D, E, F. If you know Kruskal's algorithm for finding on minimum spanning trees, if you don't know, you should learn that. I mean, minimum spanning trees are asked in almost every gate question. So if you don't know about Kruskal's and Prim's algorithm, you should learn that. So in Kruskal's algorithm, what we do is first we'll sort all the edges based on their weights. So let us say the edge weights are A, B, C, D, E, F. It can be any number. We just know that these are distinct positive weights. So let us say the sorted order is A, C, F, B, D, and E. So A, B, C, D, E, F edge weights after sorting, let us say these are the weights A, C, F, B, D, and D. What we are doing is we are increasing all the weights by the same value. So A will become A plus K, C will become C plus K, F will become F plus K, B plus K, D plus K, E plus K. Now in Kruskal's algorithm, initially how we found the minimum spanning tree was we found the sorted order, and then from that we'll choose edges one by one. So first we'll choose the edge A and add it to the minimum spanning tree, then we'll choose edge C and add it to the minimum spanning tree. Like that we'll choose every edge and add it to the minimum spanning tree such that it won't form cycle. At any point, let us say while adding F, if it forms a cycle between edges A, C and F, then we won't be adding F, we'll ignore it. We'll go to the next edge B and add it to the spanning tree in that way. That is how Kruskal's algorithm works. Now the minimum spanning tree obtained depends on the sorted order of edge weights. Now if we are increasing all the edge weights by a constant value, the new edge weight is A plus K, C plus K, etc. Now the sorted order still doesn't change. If we are increasing all the edge weights by a constant value, the sorted order between two edges doesn't change. If C is appearing before D, we can be 100% sure that C plus K will appear before D plus K in the new order. So if we are increasing all the edge weights by a constant value, the sorted order still won't change. So if we run Kruskal's algorithm again, we will be choosing this as the first edge, then C plus K as the second edge, then F plus K this as the third edge, etc. So the algorithm will work in the same way since the sorted order of edges doesn't change. So option P is true. Minimum spanning tree of G does not change on increasing all the edges by a constant weight. So the right answer is option A, P only. This is a C programming question given here. So they have given us this particular code and they are asking what the output of the program would be. So let's take a look at what it's saying here. Let's look at the main function first. We are declaring four integers, A equal to 2016, B equal to 0, C equal to 4, D equal to 42. So I have written it here. Let us say A, B, C, D, these are the variables. Inside the box I have written the values of the variables, and let us say the address of A is 100, address of B is 200, address of C is 300, and address of D is 400. Now we are calling mystery with address of A and address of B. So address of A and B are passed into this function called mystery of A. So let's see what it does here. In mystery there are two integer pointers ptr A and ptr B. So to ptr A and ptr B we are passing the address of A and B. So let's write down the variables ptr A and ptr B. The value of ptr A would be the address of A, which is 100. Similarly the value of ptr B would be the address of B, that is from here I get 200. Let us say ptr A is at address 1000 and this is at address 2000, something like this. Any address, it doesn't matter. Okay. So what we are doing here is we are declaring another variable called temp. Let us name this like this. Temp is also an integer pointer. So this is temp. Let us say that temp is at address 3000, something like this. So let us see what we are doing here. We are making temp equal to ptrb. The value of ptrb is 200. So temp becomes 200. ptrb equal to ptra. ptrb is the value of ptra. So this becomes 100. And ptra gets the value of temp, that is 200. So essentially what we did here is we are swapping the values of ptr A and ptr B. Now the value of ptr A and ptr B is the address of the variables A and B, which we passed from this function. So we are just swapping the values inside ptr A and ptr B here, as you can see clearly here. The value of the variables A, B, C, D remains unchanged. Only the value inside the pointer we are getting swapped, and these pointers are local pointers to this function. So even when we are passing A or B, the value of A and B remains unchanged, which means that whenever I am calling mystery with address A or B, with address C and C, or address A and D, whatever I am calling, the value inside A and B remains unchanged. So After every call of mystery A and B, the values of A, B or C doesn't change. So we can ignore all these calls and just print directly, print of percentage D A. And the value of A was initially 2016, that will be remaining the same as 2016. So the answer is 2016. Which of the following languages is generated by the given grammar? S gives AS or BS or epsilon. And we have been given 4 options here. So this is a question from theory of computation regarding regular or context-free grammars. So let's take a look at S here and generate a few strings and see what all strings S is actually generating. So S can directly give epsilon, that is one string, and S can give AS from this production, and this S can be resolved to epsilon. So S will give the string A in this chain. S can also give BS from this production, and this S I can resolve it to epsilon, so the string would be B. Similarly, S can give AS, which can be resolved to, this S can be resolved to BS, giving us the total production ABS, and this S I can resolve to epsilon, giving the string AB. In the same manner, I can generate strings BA, AA, BB, etc. So, which means that this S can produce A and B independent of each other any number of times. See, from S I can generate one A or one B, again A and B I can keep on generating independently until all this I can resolve to epsilon remaining. So this S is nothing but generating the language A, B star. Any string in A and B, any strings using A and B I can generate having length 0, 1, 2, etc. This is A comma B star. Now the right option is D here. Which of the following decision problems are undecidable? 1. Given NFAs N1 and N2, is language of N1 intersection language of N2 equal to 5? So this is a question from theory of computation. They have given 4 statements here and they are asking you which of the problems are undecidable. So in the first statement, for taking language of N1 intersection language of N2, what we can do is we got 2 NFAs. We can take the cross product of those NFAs and construct a new NFA and then check whether there is any accepting state and whether we can reach the accepting state. So in that way we can check whether the language of N1 and intersection language of N2 is 5 or not. So this is decidable for regular languages. Statement 2, given a context-free grammar G and a string X belong to epsilon star, does X belong to language of the grammar? So this is membership program for context-free grammars. This is decidable and the algorithm for finding out is known as the CYK algorithm. You can learn about that. So using CYK algorithm and given any X, we can find out whether that belongs to the context-free grammar G or not. So this is also decidable. 3. Given context-free grammars G1 and G2, is language of is language of G1 equal to language of G2? So this is the equality problem for context-free grammars. This is a well-known problem. This is undecidable. There is no way we can find out whether the language generated by G1 and G2 would be the same. So this is undecidable. Given a Turing machine M, is language of M equal to 5? This is again emptiness problem for recursive enumerable languages. Given a Turing machine, we can't find out whether the language is 5 or not. This is undecidable. So if you refer to the theory of computation video lectures towards the end, all such properties and many more properties for all the grammars, regular languages, context-free grammars, recursive enumerable grammars, all that is given in the video lecture. So you can learn that table there and then you can use it to answer these questions, these type of questions directly. So for this one, the answer is 3 and 4 are undecidable. They were asking which are undecidable. So the option is C. Which of the following regular expressions represents the language, the set of all binary strings having 2 consecutive zeros and 2 consecutive ones? So this is a question from theory of computation regarding regular expressions. In the question they have given us a language, the set of all binary strings having 2 consecutive zeros and 2 consecutive ones, and 4 options have been given which contain 4 regular expressions, and they are asking which of these regular expressions captures the language given here correctly. So I've written one sample string here. Now this string contains 2 consecutive zeros. It also contains 2 consecutive ones. So it contains 2 consecutive zeros and 2 consecutive ones. So this string belongs to the language given in the question. Okay, now let us look at the regular expressions given in the options and see which all can generate this string correctly. So if you look at option A, it says 0 plus 1 star 0 0 1 1 0 plus 1 star plus 0 plus 1 star 1 1 0 0 0 plus 1 star. Now this regular expression, what it gives is, it gives the set of all strings which has 0 0 1 1 or 1 1 0 0 as a substring. Now if you look at our sample string, this string doesn't have 1 1 0 0 or 0 0 1 1 as a substring, but this string belongs to the language given in the question, and this regular expression can't cover this string. So clearly this regular expression doesn't cover the language given in the question. So this is wrong. Let's look at option Z. Option C, 0 plus 1 star 0 0 0 plus 1 star plus 0 plus 1 star 1 1 0 plus 1 star. So this regular expression generates all strings which has either 0 0 or 1 1 as a substring. So if you take a look, this string is covered by this language. We can generate this string using this regular expression. But there is one problem. If you look at this part can generate even the string 0 0 or even the string 1 1 alone. So this kind of string can also be generated by this regular expression. But clearly this string doesn't belong to our language. For our language, it needs both 0 0 as well as 1 1 as a substring in the every strings of the language. So clearly this option C is also wrong. It generates strings which doesn't belong in the language. Now let's look at option D. If you take a look at option D, it generates strings starting with 0 0 and ending with 1 1, or starting with 1 1 and ending with 0 0. Again, this is also wrong. In our sample string it starts with 0 1, but it can only generate strings starting with either 0 0 or 1 1. So this is also wrong. Now the only option left is option B. So if you take a look at option B, what it says is, it starts with 0 or 1 star, that is fine. It ends with 0 or 1 star, that's also fine. And in the middle part, it will be either 0 0 0 0 0 plus 1 star 1 1 or 1 1 0 plus 1 star 0 0. Now this is correct. This generates strings which has 0 0 and 1 1 as a substring. Either 0 0 will appear first and then 1 1, or 1 1 appears first and then 0 0. Either way, it will cover all the strings that has 0 0 and 1 1 as a substring. Also, it doesn't generate strings having just 0 0 or just 1 1, this kind of string which the language in C was generating. So this is the correct answer. Consider the following code segment: x equals u minus t, y equals x into v, x equals y plus w, y equals t minus z, y equals x into y. The minimum number of variables required to convert the above code segment to static single assignment form is dash. So this is a question from compiler decide regarding static single assignment forms. So what is static single assignment form? Static single assignment form is a way of writing the code given here such that each time a variable is getting assigned some value, we must be using different names for that variable. For example, if you look at the code here we are assigning some value to x, as well as after a while we are assigning some other value to x here. So this x and this x should be having different names that we will denote by giving some unique subscript to x each time some value is getting assigned. So with that information, let us try to find out how many variables are required if you are converting this to static single assignment form. So if you take a look here, how many variables are there? There are 7 variables actually. This is which can be given as t, u, v, w, x, y and z. Okay, you can take a look and verify that there are only 7 variables given here, and among these 7 variables we are assigning value only to x and y. The other variables appear only on the right hand side, so we can just represent them using whatever representation is already here. We can just use the variable name directly because no value is getting assigned to them, so they won't need more than one variable name. So we only need different names for x and y because they are the only ones to which we are assigning some values. So let us try doing that. To x we are assigning u minus t, so let us name this x as x1. Okay, now y equals x into v. Now there is no variable called x, this one was x1 and we are immediately using the value of x1, so this will also become x1. and they are saying y equal to x1 into v. Now we are assigning some value to y. Let us call this y2. Okay, and then we are assigning some new value to x. So we'll call this x3, sorry, x2, x1 we already used up, x2 we are using here equal to y plus w. There is no y, we assigned value to y2 here. I'll be using y2 only. So I used y2 here, I will be renaming it to y1. Sorry, it was the first time I was using y. Okay, now for second time I am assigning some value to y. So here I will use y2 equals t minus z, and here I am assigning some new value to y. So I will be giving y3 equal to x, which was the latest x, that was x2 into y. So you can take a look again. X1 equals u minus t, y1 equals x1 into v, x2 equals y1 plus w, y2 equals t minus z, y3 equal x2 into y. So this is fine. This is static single assignment form of the code given in the question. So if you take a look for x, now we have x1 and x2. For y we have y1, y2, y3. So initially there were 7 variables. Now there are 1, 2, 3, 4. For x we have 2, 5, 6. For y there is 3, 7, 8, 9 and z. So there are total 10 variables now. So 10 is the minimum number of variables required to convert the above code to static single assignment form. The answer is 10. Consider an arbitrary set of CPU bound processors with unequal CPU burst length submitted at the same time to a computer system. Which of the following process scheduling algorithms would minimize the average waiting time in the ready queue? A. Shortest remaining time first. B. Round robin with time quantum less than the shortest CPU burst. C. Uniform random. D. Highest priority first with priority proportional to CPU burst length. So this is a question coming from operating systems regarding process scheduling. They are saying us that a number of processes arrive to the CPU at the same time, all of which has unequal burst lengths. If that is the case, which of the algorithms given in the options will minimize the average waiting time in the ready queue? So let's consider one example of the situation given in the question. Let us say two processes P1 and P2 arrive at the same time, and P1 has a length of 3, burst length of 3, and P2 has a burst length of 5, imagine. So we will try out these algorithms one by one. Let us try shortest remaining time first. If we choose shortest remaining time first, you can see P1 has the shortest remaining time. So P1 will be chosen first and then P2 will run. Meaning P1 will have a wait time of 0 and P2 will have a wait time of whatever is the burst length of P1. So P1 has a wait time of 0 plus P2 has a wait time of 3. So the average is by 2 equals 1.5. Now let us try longest remaining time first. Now this longest remaining time first is whatever is given in D. It's saying highest priority first with priority proportional to CPU burst length. Meaning the process having the longest burst length will have the highest priority and that process will run first. So it is same as longest remaining time first algorithm. If we choose the longest remaining time first algorithm, P2 has the longest remaining time. So P2 will run first and then P1 will run first. Meaning P2 will wait for 0 time and P1 will wait for the length of P2, that is 5. So the average waiting time would be 5 plus 0 by 2, that is 2.5. Now let us consider round robin algorithm with time quantum equal to 1. That was given in option B. Round robin with time quantum less than the shortest CPU burst. Here the shortest CPU burst is 3. I have chosen a time quantum of 1 which is less than 3. So if that's the case, for the first time quantum P1 will run. After that P2 will run, after that P1 will run, after that P2 will run, after that P1 will run. Now P1 has used up 3 time quantum, meaning P1 will be over now, meaning P2 can run freely after this. So P2 will run from, so when P1 is over the time was 5, so from 5 to 8 P2 will run freely. Now let's try to calculate the wait time here. P1 started here and P1 was ending here. In between there were 2 cycles in which P2 was running. So these 2 cycles are the wait time of P1. So P1's wait time is 2. Similarly, if you look at P2, P2 came here. So P2 started from here only, that was the arrival time, and P2 is finishing here. In between, for 3 cycles of P1, P2 was waiting. So wait time of P2 is 3. So the average wait time is 2 plus 3 by 2, that's equal to 2.5. So if you take a look at all these 3 algorithms, you will see that the one minimizing the shortest the minimizing the average wait time is shortest remaining time first algorithm. So among options A, B and D, A minimizes the average wait time. Now option C is uniform random. Uniform random means it can take a random, it can run the process in a random order. So uniform random can become shortest remaining time first or longest remaining time first, or round robin. It won't become round robin because round robin is having time quantum, right? So it won't be round robin. Uniform random can be shortest remaining time first or the longest remaining time first. So it can't guarantee the smallest average wait time. If it becomes longest remaining time first, then it will have a higher wait time. So uniform random is also not correct. So here the answer is shortest remaining time first. That's the one which minimizes the average wait time. Which of the following is not a super key in a relational schema with attributes v, w, x, y, z and primary key vy? So this is a question from DBMS section. They have given that for this schema vy is the primary key, and they have given us 4 options, and they are saying which of the following is not a super key. So if vy is the primary key, then for whatever super key we take, vy will be a subset of that. That is, whatever super key options we have, v and y both should be containing in that. So if you take a look at option A, it has v and y, so that's correct. Option B has only v, it doesn't have y, so we can't say that this is a super key. Option C, v and y is there. Option D also v and y is there, meaning B is the one which is not a super key because it doesn't have y in it. So B is the answer to this question. Which of the following is not a part of the ACID properties of database transactions? A, atomicity, B, consistency, C, isolation and D, deadlock freedom. So this is a straightforward question coming from DBMS sections. So if you have learned transactions in DBMS, the first thing you learn is the ACID properties. A transaction in a database system must maintain A, atomicity, C, consistency, I, isolation and D, durability. This is what is commonly known as ACID properties. So they are asking directly from this. If you look at this, D is durability. In the options they are given, this has deadlock freedom. So deadlock freedom is not a part of ACID properties. So this is the answer. A database of research articles in a journal uses the following schema: volume, number, start page, end page, title, year, price. The primary key is volume, number, start page, end page. The following functional dependencies exist. Volume, number, start page, end page gives title. Volume and number gives year. Volume, number, start page, end page gives price. The database is redesigned to use the following schemas now: volume, number, start page, end page, title, price, volume, number, year. Which is the weakest normal form that the new database satisfies but the old one does not? So this is a question from database management system regarding normalization. So they have given that initially we had a schema of volume, number, start page, end page, title, year and price, and the primary key is volume, number, start page, end page. So I will mark it as this: volume, number, start page, end page. So this is the primary key now, and they are saying the following functional dependencies exist. So let us have a quick refresher of what the condition for each normal form is. So for a database to be in second normal form, no partial key to non-keys functional dependencies are allowed, meaning that if there is any functional dependency which is of the form partial key to a non-key attribute, partial key attribute is some attribute which is part of the primary key but it doesn't form the full primary keys, which is partial key, and non-key means it is an attribute that doesn't belong in the primary key. So no partial key to non-key dependencies are allowed in 2NF form. A database is in 3NF if no non-key to non-key functional dependencies are there. So if there is any functional dependency which is of the form non-key to non-key, then it is not in 3NF form. In BCNF, all dependencies must be of the form super key to something. So if all the dependency in a database is of the form super key to something else, then that database is in BCNF. Now let's take a look at the functional dependencies and see this schema is in which normal form. So first one is volume, number, start page, end page. Now this is the primary key. Primary key was the same thing: volume, number, start page, end page. So this schema, this functional dependency is of the form primary key to something else. So this satisfies the BCNF condition. So this alone we can say this satisfies the BCNF condition. The second one is volume, number to year. So volume and number both are part of the primary key. Volume and number is there, but it doesn't form the full primary key. So this is a partial key. From partial key we have a dependency to year. Year is not a part of the primary key. So year is a non-key attribute, meaning we have a functional dependency of the form partial key to non-key, meaning this violates the 2NF condition. So this is not in 2NF, meaning this is in 1NF. Now volume number start by n page, this is primary key to something else. So this satisfies BCNF condition. But if you see, there is one functional dependency which violates 2NF condition. So this schema is in 1NF. This is the weakest form, right? So this schema is in 1NF. Now they are saying the database is redesigned to use the following schemas. One is volume number, start page, end page, title, price. So the primary key is entirely there here, the initial primary key, volume number, start page, end page, that is there in this table. And these functional dependency, volume number, start page, end page to title, volume number, start page, end page to price, both exist in this schema. So these both were in BCNF form. So this schema satisfies BCNF. This table satisfies BCNF. Now look at the next table, volume number year. So if you take a look in this one, initially the primary key was volume number, start page, end page, but start page and end page attributes doesn't exist in this one. So in this one there is only volume and number, and volume and number gives year was a functional dependency, so that exists inside this. So for this table, volume and number will be the primary key. Now volume number gives year, functional dependency exists inside this, but volume number is not partial key now, since in this table the primary key is volume number only now, since start page and end page is not there in this table. So this functional dependency volume number gives year is of the form primary key to something else. This satisfies BCNF condition. So this schema as a whole, if you can see, this is in BCNF, this is in BCNF. So this schema as a whole is in BCNF, but the initial schema was in 1NF. So the question was, what is the weakest form that the new database satisfies, but the old one does not? So this is in BCNF, means this is also in 3NF and also in 2NF, but this was only in 1NF. So the weakest form this one is in, that this one doesn't satisfy, is 2NF. So the option is B, 2NF. That's the correct answer. Which one of the following protocols is not used to resolve one form of address to another? A. DNS, B. ARP, C. DHCP, D. RIRP. So this is a question from computer networks regarding the protocols given here. So we'll go through these protocols one by one. The first one is DNS, or domain name system. Now DNS is used to resolve host name to its corresponding IP address. If you are typing google.com in your web browser, that gets resolved to its own IP address of Google server. So the protocol used for that is called DNS. It resolves host name to IP address. The second one is ARP, or address resolution protocol. Now what ARP does is, if a system in a network knows the IP address of another system but doesn't know its MAC address, then in order to resolve the IP address of the destination system to MAC address, the system uses the protocol called ARP. So it resolves IP addresses to MAC address. Reverse ARP. Now reverse ARP does the exact reverse of whatever was done by ARP. So what it does is, if you know the MAC address of a system and you need to resolve it to its IP address, RARP is used, i.e. it resolves MAC address to IP addresses. Now DHCP. Now DHCP won't be doing any resolution of one address to another. What DHCP is used for is to assign IP addresses dynamically to a new system connecting to a network. If you have your phone and you connect it to a Wi-Fi router, then the router will assign your phone some IP address, initial IP address. So that is done by using the protocol called DHCP. So from among the options, DHCP is the only one which is not used to resolve any form of address to another. So the answer is C, DHCP. Which of the following is or are examples of stateful application layer protocols? 1. HTTP, 2. FTP, 3. TCP, and 4. POP3. And 4 options are given. So what's a stateless protocol? A stateless protocol is a communication protocol in which no information is retained by the sender or receiver and treats each request as an independent transaction that is unrelated to any previous request. So in a stateless protocol, there won't be any information retained about the sender or receiver on either side. And whenever a new message is come, it will treat that message as an independent transaction only, irrespective of whatever previous messages it may have received. So examples of stateless protocols are IP, HTTP, etc. And examples of stateful protocols are FTP, SMTP, POP3, TCP. All these protocols will be retaining some information on the server side. So from the options given here, only HTTP is stateless, FTP is stateful, TCP is stateful, POP3 is also stateful. But in the question they were asking which of the following is or are examples of stateful application layer protocols. Now TCP is not an application layer protocol, only FTP and POP3 are the application layer protocols, meaning 2 or 4 are the right answers. That is option C, 2 and 4 only. The coefficient of x power 12 in x cube plus x raised to 4 plus x raised to 5 x plus x raised to 6 etc. the whole cube is dash. So we have given this expression in x, that is x cube plus x raised to 4 plus x raised to 5 plus etc. and the cube of this, and they are asking us to find out the coefficient of x raised to 12 in this expression. So let us try to expand this. So the series is what? X cube plus x raised to 4 plus x raised to 5 plus x raised to 6 plus etc. into the same thing into the same thing. Now let us try to expand this. For expanding this, let us take the first term x cube from here and we'll multiply it with the first term here. So now it already became x cube into x cube, that is x raised to 6, and they're asking us to find the coefficient of x raised to 12 only, right? So we'll only find out terms with x raised to 12 only here. So we already got x raised to 6. Now we need to multiply it with x raised to 6 in order to make it x raised to 12. So we have already taken x cube, and from here I need to take x raised to 6 in order to make the total coefficient x power 12. If I am taking x cube and x cube from these two sets, there is no other value of x which I can take other than x raised to 6, which will make coefficient x power 12. So x3, x cube, x raised to 6 plus, now let us try to take the second one from this set, x cube into x raised to 4. If I do x cube into x raised to 4, the coefficient is already 4 plus 3, 7. Now if I multiply it with x raised to 5, it will be x raised to 12 totally. So from this set I have no other choice than to take x raised to 5 only. So I will be taking x cube into x4 into x raised to 5. Similarly, I'll take x cube into the third one from this set, x raised to 5 into x raised to 4. Similarly, again I'll take x cube into the fourth one from this set, that is x raised to 6. Then I'll have to take x cube from the third set. Now if I take x cube from the first set and x raised to 7 from the second set, already the coefficient is x raised to 10. In order to make the total x raised to 12, I will have to take x square from this set if I am taking x cube and x raised to 7 from here. But as you can see, x square is not there in this set. So if I take x cube and x raised to 7 from these two sets, then even the smallest x I can take is x cube, which will make it x raised to 13. So that won't be an x raised to 12 term, so we don't have to worry about that. So we'll stop at this point for x cube taken from the first set. Now I'll take x raised to 4 from the first set. I'm taking x raised to 4 from the first set. Let us suppose I take x cube from the second set. Then the total power is 4 plus 3 equal to 7. Now remaining is only 5 in order to make the total 12. So I will take x raised to 5 from the third set. Similarly, x raised to 4 into x raised to 4 into x raised to 4 plus x raised to 4 into x raised to 5 into x cube. After that, if I am taking x raised to 4, if I take x raised to 6 from here, there is no way I can make x raised to 12 by taking some term from here. So I will stop at this point. Similarly, I will take x raised to 5 and see x raised to 5 from the first set into x cube into x4 plus x raised to 5 into x raised to 4 into x raised to 3. These two are the only possibilities if I take x raised to 5 from the first set. Similarly, if I am taking x raised to 6 from the first set, I have to take x raised to 3 from the second set and x raised to 3 from the third set. That's the only possibility if I am taking x raised to 6 from the first set. So these are the total multiplications which I can do in order to get x power 12. So the total expression, when I am expanding, I will get all of these for x raised to 12 plus the rest of the terms which when I multiply, which you can try and get the rest, but we don't need that for the question. So for x raised to 12, there are how many terms here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So adding this, I will get 10 x raised to 12. But if I take any other combination, I will be getting some x value which is not equal to x raised to 12. So the coefficient of x raised to 12 is 10, and 10 is the answer to this question. Consider the recurrence relation a1 equals 8, an equals 6n square plus 2n plus an minus 1. Let a99 equals k into 10 power 4. The value of k is dash. So this is a question regarding recurrence relations coming from engineering mathematics section. So for the given recurrence relation, they are asking us to find out a99. a99 will be k into 10 power 4, and they want us to find the value of k. So basically they want us to find the value of a99 only here. So let's try to write down each numbers in the series. So a1 will be equal to 8. It's given in the question. a2 will be 6n square plus 2n plus an minus 1, where n equal to 2. That is 6 into 2 square plus 2 into 2 plus a1. Now a3 would be 6 into 3 square plus 2 into 3 plus a of 2. Now a of 2 I will rewrite it as 6 into 2 square plus 2 into 2 plus a1. So if you take a look here, you will see that a3 is 6 into 3 square plus 2 into 3 plus 6 into 2 square plus 2 into 2 plus we have a1 here. So 6 into n square plus 2 into n, and 6 into n minus 1 square plus 2 into n minus 1. Similarly, we can form a pattern here, right? Only problem is that we have one a1 term here. Now let us see if we can write a1 also in terms of 6 and 2 in this format. So a1 is 8, right? So 8 we can rewrite it as 6 into 1 square plus 2 into 1. 6 into 1 square is 6 plus 2 into 1 is 2. So now it is correct. a1 is 6 into 1 square plus 2 into 1. a2 is 6 into 2 square plus 2 into 2 plus, instead of this I will write 6 into 1 square plus 2 into 1. a3 is 6 into 3 square plus 2 into 3 plus 6 into 2 square plus 2 into 2 plus, instead of a1 I will write 6 into 1 square plus 2 into 1. See, now we have a pattern here. I can now write an will be equal to 6 into n square plus 2 into n plus 6 into n minus 1 square plus 2 into n minus 1 plus 6 into n minus 2 square plus 2 into n minus 2, etc. up to 6 into 1 square plus 2 into 1. Or I can rewrite it as, I will take the 6 common here, 6 into n square plus n minus 1 square plus n minus 2 square, etc. up to 1 square, plus these two terms will, from there I will take 2 as common outside, 2 into n plus n minus 1 plus, etc. up to 1. So again rearranging this, we will get 6 into 1 square plus 2 square plus 3 square, etc. up to n square, plus 2 into 1 plus 2 plus 3, etc. up to n. Now sum of the series 1 square plus 2 square plus 3 square, etc. up to n square will be n into n plus 1 into 2n plus 1 by 6. That is well known. So that I will write here 6 into n plus 1 into 2n plus 1 by 6. The 6 and 6 I can cancel out. Similarly for this part, 2 into 1 plus 2 plus 3, etc. up to n. 1 plus 2 plus 3, etc. up to n is n into n plus 1 by 2. So this will be 2 into n plus 1 by 2. This 2 and 2 I can cancel out. So we got the term for an. an will be n into n plus 1 into 2n plus 1 plus n into n plus 1. Now for a99 we will write that here. a99 will be equal to n into n plus 1 into 2n plus 1 plus n into n plus 1. That is 99 into 99 plus 1 into 2 into 99 plus 1 plus 99 into 99 plus 1. 99 into 99 plus 1 becomes 100. So this will be 9900. So this term is 9900 into 2 into 99 is 198 plus 1 is 199. So this is 9900 into 199 plus again 99 into 99 plus 1 is 100. That is 9900. So 9900 I can take common. This will be equal to 9900 into 199 plus 1. That is 9900 into 200, which is nothing but 198 into 10 power 4. Now we have found out a99, that is 198 into 10 power 4. In the question it was given that a99 is k into 10 power 4 and we had to find the value of k. So clearly the value of k is 198. That's the answer. A function f from n plus to n plus defined on the set of positive integers n plus satisfies the following properties. F of n equals f of n by 2 if n is even. F of n equals f of n plus 5 if n is odd. Let R equal to set of all elements I such that there exists j, f of j equals I, be the set of distinct values that f takes. the maximum possible size of R is dash. So this is an interesting question coming from engineering mathematics in set theory. So they have given us a function f that is defined from the set of positive integers to the set of positive integers. So domain and range are both same here, and this function satisfies these following properties. F of n equals f of n by 2 and f of n equals f of n plus 5. This if n is even and this if n is odd. So please note that they are not saying f of n equal to n by 2, they are saying f of n equals to f of n by 2. Okay, and they are given this set R equal to set of elements I such that there exists j, so set f of j equal to I. So this is nothing but the set of distinct values that the function f can take. Okay, so they are asking what is the maximum possible size of set R. So let us rewrite these properties again here. So if f of n is odd, f of n will have the same value as f of n plus 5 that is given in the question here. Also f of 2n. Why I have written this is f of, consider the value of f of 2n. Now you know 2n is even, obviously, because 2 is a factor, right? So for f of 2n will have the same value as f of 2n by 2 that is given here in the question. If n is even, it will have the same value as f of n by 2. So f of 2n will have the same value of f of 2n by 2, that is nothing but n. So if n is odd, we can write f of n plus 5, and f of 2 into n will also have the same value as f of n. Similarly, if n is even, f of n will have the same value as 1 f of n by 2 that is given in the question if n is even. F of 2n, that's because just like we did here, 2n is obviously even, meaning f of 2n will have the same value as f of n here. Also f of n minus 5. Why I have written this is if n is odd, f of n will have the same value as f of n plus 5. Now if n is odd, n plus 5 will always be an even number. So f of n plus 5 will have the same value as f of n when n plus 5 is even, so that I can rewrite as f of n when n is even will have the same value as f of n minus 5. Okay, so I have written these values here. Now let us try to find out what all distinct values the function f can take. Now I have written it in a graph form here, so it's not a graph question, I have just written it so that I can join all the values which have all the f values which has the same value, and I can put it together in a easily readable form. Okay, so let this node represent the value of f of 1. Okay, it can be any value that is not given in the question. F of 1 can be anything. So let us take some value f of 1 denoted by this circle here. Now f of 1 will have the same value as when n is odd, f of n plus 5 and f of 2n. Okay, so f of 1 will have the same value as f of 1 plus 5 is 6 and f of 1 into 2 that is 2. Okay, so I am just writing here what I have written in this graph means that all the nodes here will have the same value for f of that value. Okay, so f of 1 has the same value as f of 6 and f of 2. Now let us take 6 here. 6 is even, meaning f of 6 will have the same value as f of 3. So I have drawn a node for that and I am joining it here. F of 6 will have the same value as f of 3. F of 6 will have the same value as 2n, that is 12. Also it will have the same value as f of n minus 5, that we have already started, right? F of 1, it's already there. So let's take a look at 2. It's also even, it will have the same value as 2 by 2, 2 into 2 and 2 minus 5. So this f of n will have the same value as f of n minus 5 only if n minus 5 belongs to the set n plus, right? So 2 minus 5 is a negative value, so that doesn't belong to the set n plus, so I won't be writing this part here. So f of 2 will be having the same value as 2n, right? So it will have the same value as 4. Now if you take a look at this 4, you will see that f of 4 will have the same value as f of 8. Similarly, this I can keep on drawing it by multiplying it by 2, keep on drawing it like that here. Now for 6 we are already found out that f of 6 will have the same value as f of 12. 12 is even, so it will have the same value as 12 minus 5. So I can write the bubble for f of 7 as well. Similarly, f of 7 will have the same value as 2 into 7, that is 14. F of 14 will have the same value as f of 14 minus 5, that is 9. So I can keep on drawing it like this and I will get a bunch of values which belong together, right? So if you see, none of the numbers here are a multiple of 5. So there is no property, and I have just kept on drawing this and I just found out that none of the numbers here are a multiple of 5, right? So I will start a new bubble for 5. Let us say this bubble represent the value of f of 5. So f of 5 is an odd number, so I can write 2n as well here. So f of 5 will have the same value as f of 10. F of 10 will have the same value as f of 20. F of 20 will have the same value as f of 40, etc. F of 20 will also have the same value as f of 20 minus 5 as given here. So 20 will have the same value as 20 minus 5, that is f of 15. 15 will have the same value as 15 into 2, that is 30. 30 will have the same value as 30 minus 5, that is f of 25. Similarly, I can keep on drawing here. So what you will see here is that once I keep on expanding it, this will cover all the multiples of 5, that is 5, 10, 15, 20, etc. All the numbers here will have the same value for the function of that number. F of 5, f of 10, f of 15, 20, etc. will all have the same value. Similarly, if you take a look here, 1 is here, 2 is here, 3 is here, 4 is here. Now 5 belongs in this set, 6 is here, 7 is here, 8 is here, 9 is here, 10 belongs in this set, right? So we can stop at this point, we can keep on drawing it and find out, but what we'll see is that all for n which is not a multiple of 5, f of n will have the same value, and if n is a multiple of 5, it will have a different value. So f of 1 and f of 5 are our starting points. So if we assign f of 1 some value and f of 5 a different value than f of 1, we will see that the f can take a maximum of 2 distinct values, that is one value for all of these and one value for all of these. If f of 1 and f of 5 we were taking the same value initially, then all n will have the same value only. So in the question they have asked us the maximum possible size of n. So the maximum possible size of n is, as you can see, there are only 2 sets here, that is 2. So 2 is the answer to this question. Consider the following experiment. Step 1, flip a fair coin twice. Step 2, if the outcomes are tails, heads, then output y and stop. Step 3, if the outcomes are either heads or heads tails, then output n and stop. Step 4, if the outcomes are tails, then go to step 1. The probability that the output of the experiment is y is dash. So this is a question from probability theory. Here they have given an experiment in these following steps given here. So they are saying we are flipping a coin twice, and if the outcome is tails, heads, then we'll output y. If the outcome is heads or heads tail, then we'll output n. And if the outcomes are tails, then we'll repeat the experiment again. So if the outcomes are tails, heads tail, or heads, we'll be printing yes or no and then y or n, and then we'll be stopping the experiment there. But if the outcomes are tails, then we'll be going to step 1 again, that is we'll be repeating the experiment again. So let's find out the probability of each of the outcome in the experiment. So tails, heads is one of the outcomes, heads, tails, tail, tails. Now they are given it's a fair coin, right? So each of these outcome will be having a probability of 1/4 associated with it. Each of the outcomes are a key probable, so it has a 1/4 probability for each of those. So if tails head appears, then we'll be printing y. If heads tail or heads is appearing, then we'll be printing n. And if tails is appearing, then we'll be repeating again. So in the question they have asked us what is the probability that the output of the experiment is y. Now probability that the output of the experiment is y is same as the probability that we'll be printing y in the first step, plus the probability that we'll be printing y in the second step, plus the probability that we'll be printing y in the third step, etc, etc. So for an output y to appear, we can either print y in the first step itself, we get y, we get tail head and we print y, or we get a repeat this part, repeat outcome, and then in the second trial we get y, or we get a repeat first, and second time also we get repeat, and the third time we get y. Similarly we can keep on doing it like that. So the sum of all those will be the probability that the outcome is y. Now probability that it is y in the first step is tail set, that is 1/4. Probability it is y in the second step is we get repeat in the first step and we get y in the second step, that is 1/4, which is the repeat outcome, into 1/4, which is the print y outcome. Similarly 3 times, that is we get repeat 2 times, that is 1 by 4 into 1 by 4, and the third time we get output y, that is 1 by 4. So this is nothing but the geometric series 1 by 4 plus 1 by 4 square plus 1 by 4 cube, etc. That is same as geometric series a plus r a plus r square a, etc. Now the sum of this series will be a by 1 minus r, since r is less than 1. So I have rewritten that here. This is the sum of the series is a by 1 minus r. A was 1 by 4, r also was 1 by 4. Now that's equal to 1 by 4 divided by 3 by 4. That is 1 by 4 into 4 by 3. That is 1 by 3. So for the question, the answer is 1 by 3 or 0.33. That's the answer here. Consider the two cascaded 2 to 1 multiplexers as shown in the figure. They are given two by 1 multiplexers cascaded as shown here. The minimal sum of products form of the output X is, and we have been given 4 options. So this is a very straightforward question coming from digital logic section regarding multiplexers. So in the question they are given us two by 1 multiplexers as shown here. It is cascaded together, and they are asking us what would be the expression for the output X here. So if we have a 2 by 1 multiplexer like this, and we have the inputs A and B, okay, and if X is a select line provided to this, then the output Y, the Y's expression would be Y equal to, when X is 0 it will be printing A, and when X is 1 it will be outputting B. So that we can rewrite as X complement into A plus X into B. So for this given multiplexer here, the output expression for Y would be X complement A plus XB. So based on that information, let us look at the question here. So to the first question, the select line is P and the input is 0 or R. This is not O, this is 0 and this is R. So the expression for this part would be it is the output of the first multiplexer. That would be P complement into 0 plus P into R. Now this is 0, this term gets cancelled out, so the expression would be PR. That is the output of the first multiplexer. Now that is given as input to the second multiplexer, and here Q is the select line. So the expression for X would be Q complement into R complement is the input here, plus Q into whatever was the input here, that was PR. So it would be Q complement into R complement plus Q into PR, that we can rewrite as PQR. So this is the answer. If you take a look at the options, you will see that is option D given there. The size of the data count register of a DMA controller is 16 bits. The processor needs to transfer a file of 29,154 kilobytes from the disk to main memory. The memory is byte addressable. The minimum number of times the DMA controller needs to get the control of the system bus from the processor to transfer the file from the disk to main memory is dash. So this is a question coming from computer organization regarding DMA or direct memory access. If you don't know about DMA, please refer to the video lectures for DMA in the computer organization topic, and you can learn about that before answering the question here. So to roughly explain what DMA is a mode of performing input-output from the peripherals to the main memory without involving the processor in between. So here they haven't given us any details about the mode of operation of the DMA. So here we will be assuming that the DMA is operating in burst mode. So in burst mode, what happens is, for each byte of data transferred, we have a count register. Okay. So in count register, there will be a count of how many bytes of data is to be transferred, and after transferring each byte of data to the main memory, we will be increasing the count register by 1 or decreasing the count register by 1. So whatever is the size in count, let us say if count is showing 5, then we will be transferring 5 bytes from the peripheral to the main memory. Now here they have given us that the count register size is 16 bits, meaning the largest possible number that can be stored in the count register is 216, which means that in one round up to 216 bytes of data can be transferred, because after transferring each byte we will be reducing the value in count register by 1. Okay, so we can transfer 2 raised to 16 bytes in one round. So 216 bytes is nothing but 64 KB. So the size of the file which we needed to transfer was 29,154 KB, and in one round we can transfer up to a maximum of 64 KB only. So total number of rounds needed would be 29,154, that is the size of the file, divided by 64 KB, that is what data we can transfer in each round, that is 455.53. Now they are asking how many times we need the controller, the DMA controller needs control, right? So that should be an integer, so it should be the upper value of this, that is 456, that's the answer. The stage delays in a 4-stage pipeline are 800, 500, 400 and 300 picoseconds. The first stage with 800 picosecond delay is replaced with a functionally equivalent design involving two stages with respective delays 600 and 350 picoseconds. The throughput increase of the pipeline is dash percentage. So this is a question from computer organization regarding pipelining. If you don't know about pipelining or don't know about solving questions coming from pipelining section, please refer to the video lectures for those first and then come back to this. So here in the question we have been given two pipeline implementation. In the first implementation there are 4 stages and each having a delay of 800, 500, 400, 300 picoseconds, etc. And in the second implementation this stage has been split into 2 independent stages having 600 and 350 delay, and then the rest of the 3 stages are the same, 500, 400 and 300. So if you take the time for running one instruction, you will see that this one, the first implementation will run it faster than the second implementation, because here it is 800, instead of that we have 600 and 350, totally 950 delay here, and the rest of the delays are the same. So for running one instruction the first implementation would be faster, but when we are running a large number of instructions, you will see that each instruction will take only one cycle time to run the instruction. So as we have a large number of instructions running, each instruction will approach 1 cycle per instruction time. So if you look in the first implementation, the cycle time would be the time of the slowest stage here. So here the cycle time is 800 picoseconds. In the second implementation the slowest stage is 600. So the cycle time is 600 picoseconds in the second implementation. So when we have a large number of instructions, each instruction in the second implementation will take only 600 picoseconds to run, but the first one will take 800 picoseconds to run. So when we have a large number of instructions, the second implementation will become faster. So the new throughput of the second one compared to the first one would be the time for running the time for each instruction for the first implementation divided by time for each instruction for the second implementation, that is 800 by 600, that is 133.33%. So this one has a 133.33% throughput compared to the first one. So the increase in throughput is this minus 100, that is 33.33% increase, meaning the second implementation is 33.33 times faster than the first implementation. The answer they were asking, the increase percentage, that is 33.33. Consider a carry lookahead adder for adding 2 n-bit integers built using gates of fan-in at most 2. The time to perform addition using this adder is dash, and 4 options have been given. So this is a straightforward question coming from digital logic section regarding carry lookahead adder. So the standard formula for the time complexity of a carry lookahead adder is theta log of n to the base k, where n is the number of bits to be added and k is the fan-in of the gates. Fan-in means how many inputs we can give at the same time to the gates. So to see how we got the derivation of this, please refer to the video lectures regarding carry lookahead adder. So this I can directly apply here. They are given fan-in is at most 2, so this will be log n to the base 2, that is option B. The following function computes the maximum value contained in an integer array P of size n. The code snippet has been given. We have a missing loop condition here. The missing loop condition is dash, and 4 options have been given. So this is a C programming question. We have given us this function which computes the maximum value contained in an integer array P. Okay, and this is the implementation given in the function. They are asking us among these options when we apply the right missing condition, which is the right missing condition, which when we apply this function will return the maximum value contained in that integer array P. So let's take a look at this function and see what it does here. So we are passing the array P here and an int n, where n is the size of the array, and it said that n is greater than or equal to 1. So we don't need to worry about passing empty array or anything here. So at least size 1 array is passed here, and it is given A is 0, B is n minus 1. So here we are making A pointing to the start of the array and B is pointing to the end of the array. A is pointing to the first element in the array, B is pointing to the last element in the array. And there is some while condition. Inside that, if P of A is less than or equal to P of B, A is A plus 1, else B is B minus 1. And at the end we are returning P of A. So at the end we are returning P of A, meaning the maximum value should be P of A. So we need to find out the index A, which will give the maximum value in the array P. So let's assume P of A is somewhere here. Now in the loop, what it is doing, in every loop either this statement or this statement will run. If this statement is running, we will be increasing A's value by 1, meaning A moves to the right side. If this statement is the one that is run, which means B is B minus 1, meaning B we are reducing it by 1, or B is moving to the left side. So after, in every loop, A will either move to the right side or B will move to the left side. This will keep on happening until some point where A becomes the maximum value here. So clearly the ending part would be when A and B meets, right? If you take a look at the option, if A is not equal to n, then we can see, we can keep on reducing B going on, and B might move to the end of the, B might move even less than end of the array, right? B can move to the left side, reach the end, and then can go outside bound if we are using a condition like A not equal to n. If you are using a condition like B not equal to 0, B will keep on reducing and reach till the end, but A can keep on increasing and go beyond the right side of the array as well, right? And if B is greater than A plus 1, this might work, this might also work. So we just need to look at option C and D here. So now let us see what's actually happening here as well. If P of A is less than or equal to P of B, if this element is less than or equal to this element, meaning this element is at least greater or equal to this element, so the maximum element might be this. It is definitely not this. That's what we know. If P of A is less than or equal to P of B, then we are increasing A by 1, meaning we are removing this element from our equation here. We are no longer considering this element. We are going here. Similarly, if P of A is greater than P of B, this element is greater than this element, right? So this element is definitely less than this, so we don't need to consider this anymore. So we are reducing it somewhere here. So finally we'll return P of A. That means A and B should be pointing to the same element at the end. At that point we can say for sure that that element is the maximum. So if you look at the option, that is clearly this one, B not equal to A. If you are using this condition, B greater than A plus 1, let us say A is 2, then and B is 4, B greater than A plus 1. So there is one mistake with this one, B greater than A plus 1, meaning initially itself this condition is satisfied. So we might not even look at many elements in the middle of the array into consideration for the while loop. So this also was wrong. This is the only answer, B not equal to A. Why that is the correct answer is, when this condition is satisfied, A and B will be pointing to the same element, and that will be the maximum. Until that, A and B will be pointing to the different elements, and we need to consider this part if P of A less than or equal to P of B. Till that happens, till A becomes equal to B. So the condition is B not equal to A. This is a C programming question here. In the question they have given us this particular code snippet, and they are asking what the output of the following program would be when in the main function we are calling count of 3, and 4 options have been given. So let's take a look at how the function calls proceed. So initially we are calling count of 3. Okay. So in the count function, what you need to see is that D here is a static integer, meaning there is only one instance of D associated with the entire program. Unlike, so we won't be, in every function call of count, we won't be having distinct D's, but we'll only be having one single instance of D. Unlike n, where n is a local variable to the function. So let's, based on that information, let's look at how it proceeds. So initially we are calling count of 3. So here n is 3. D we are assigning to 1 since this is the first call. We are printing n and D, so n is 3. After that we are printing D, D is 1. So 3 and 1 would be printed. After that we are incrementing D. So D was 1 initially, now it's incremented to 2. After that we are calling count of n minus 1, that is count of 2. So we are calling count of 2 here. Now you need to see that we haven't exited from count 3 function. This function we haven't exited, but within this function only we are calling count of 2 recursively. Okay, so we are in count of 2 now. we are printing n, that is 2. After that we are printing d, so d is 2 now, so 2 will be printed. After that we are incrementing d again, so d will be incremented to 3 now. If n is greater than 1, that is true, 2 is greater than 1, we are calling count of 2 minus 1, that is count of 1. So we will be calling count of 1 here. We are printing n is 1. After that we are printing d, so d is 3 currently, so 3 will be printed. After that d is incremented, so d becomes 4 now. If n is greater than 1, that is false, so we won't be calling count again since n is 1 now. We will be printing this statement directly, so print d. D is 4 now, so 4 will be printed. After that we will exit from this count function. We will be coming to this count function, so we were at this statement. Now this statement will execute, that is printf of %d. D is 4 now, so 4 will be printed. After that we will exit from count of 2, we will come to count of 3 function. There is only one more statement left, that is again printing d. So d will be printed and we will exit from this and the program will exit. So if you look at the output printed is 3 1 2 2 1 3 4 4 4. That is option A. What will be the output of the following pseudocode where parameters are passed by reference and dynamic scoping is assumed? The pseudocode given here is a equal to 3, void n of x, x equal to x into a, print x, void m of y, a equal to 1, a equal to y minus a, n of a, print a, void main, m of a. And 4 options have been given. We need to find out which among these options will be printed when this is run. So this is not a C programming question. So here what they have given us is pseudocode and they are saying that it is passed by reference and we need to assume dynamic scoping. Since it is dynamic scoping, it is not C programming. If it was C programming, they would have used static scoping. So let us try to see what happens here. First, here we have an a equal to 3. Now that is a global a, so we'll call it global a. There's a global variable a. Now inside the main function I am calling m of a, we are calling m of a. So since no other a has been declared so far, this a will be the global a only. So the global a is being passed to this function void m of y. Now they are saying it is being passed by reference, right? So the address of this a was being passed to y. So y and a is the same thing only. So I'll put it in a comma like this. So y and a are referring to the same variable only, y and global a, and global a was what was passed here. So the value of global a is 3, which was assigned here. Now let's come to this function. Inside that they are doing a equal to 1. Now this is again as declaring a new variable. So we will call this variable a local a. I created a container. Now the value is 1. So we have two a's now. One is global a whose value is 3 and local a whose value is 1. And y and global a are the same thing now. Here we are doing a equal to y minus a. So y is 3. The a being referred here is local a. So the local a becomes y minus, that is 3 minus 1. That becomes 2. So the local a has become 2 now. Okay. Now we are calling n of a. This local a's value is being passed to the n function. And this a is being passed by reference. So x and local a are the same thing now. They are pointing to the same variable. So local a and x is the same. X has value 2 now. And here we are doing x equal to x into a. Now what is this a? It can be either global a or the local a here. In the question they have clearly given that it is dynamic scoping, right? So initially we had a main function. Inside the main function we are using an a, that was global a here. We are using global a inside main. From inside main I am calling m. Inside m we declare another local a. And from inside m I am calling n. So inside n there is another a. So the nearest one is local a, right? So since it is dynamic scoping, we will be directly using this a's value, that is local a's value here. If it was C program, it would have used dynamic scoping. So here it would have referred to this global a only. Since it is dynamic scoping, here a means local a. Now local a's value is 2, since we can see here, and x is also the same thing, x is also 2. So x becomes x into 2. So x will be 2 into 2, that is 4, and we are printing x. So 4 will be printed first. After that we'll exit from n function, we'll come here, and then we are printing a. Now a is local a here. Local a's value has now become 4 since we had passed it by reference. So 4 will be printed again. We'll exit from here, we'll come to main, and then we'll exit. So 4 is the value which would be printed. That is option D. An operator delete I for a binary heap data structure is to be designed to delete the item in the ith node. Assume that the heap is implemented in an array and I refers to the ith index of the array. If heap tree has a depth d, that's the number of edges on the path from root to the farthest leaf, then what is the time complexity to refix the heap efficiently after the removal of the element? And 4 options have been given here. So this is a question from data structures regarding binary heaps. So if you have learned heap sort, then this question becomes very easy. It's just a minor tweaking on the heapify procedure which we apply during heap sort. So let's take a deeper look at the question. We need to implement this function delete I, which will delete the ith node, meaning we already know the index of the node which we have to delete, and then we just need to delete that node and then refix the binary tree. So let us say this is a sample binary heap, and let us say I need to delete this particular node. So this will be I. So we already know the index of the node. I just need to delete it now. So one procedure which I will do is I can just delete this node. After that I will take the farthest leaf from the binary heap, that is this one. I will take this one and swap it here. Okay. After that I can just apply heapify procedure on this node. Heapify procedure you can learn while learning heap sort. So once I swap the farthest leaf with the deleted node, and when I apply heapify procedure, that tree will be again refixed and we got a new binary heap by deleting this. So let's take a sample. Let us say the binary heap looks like this: 1 2 3 4 5 6 7. Okay, and let us say I need to delete the node 1. So I will delete this. This is the farthest node, that is farthest leaf is 7, so I will remove 7 and put it here. So 7 will be appearing here. Now there is one less element in the heap, and then I will apply heapify procedure on 7. So applying heapify procedure means at each node I will be taking the node, I will be taking the 2 children, and whichever is smaller I will swap it with that. So 2 is smaller here, so 2 will go here, 7 will go here. Again apply heapify on this node. We'll take the smallest of these two, that is 4. I'll put 4 here and put 7 here. So the final heap will look like this: 2 4 3 7 5 6. That is one element less, and this you can verify it's a binary heap. So we just need to apply heapify procedure once along any path from root to leaf. The maximum depth is d, so the total time complexity will be O of d. That is given in option B. B is the right answer. Consider the weighted undirected graph with 4 vertices where the weight of edge ij is given by the entry wij in the matrix W. The matrix is given here. The largest possible integer value of x for which at least one shortest path between some pair of vertices will contain the edge with weight x is dash. So this is a question from data structures regarding graphs. So they have given this particular graph and they are asking what can be the largest value of x such that at least one shortest path between some vertices will contain the edge of weight x. Now let's take a look at the graph here. I have redrawn the graph here in a better form. So the nodes are 1, 2, 3, 4, and the edge weights I have obtained directly from the graph. For example, edge weight from 1 to 2 is given by the entry 1, 2, that is 2. Similarly, I have drawn the entire graph. So now let's consider the shortest path without considering this edge x. Let us say this edge x doesn't exist, and let us try to find out the shortest path. The shortest path from 1 to 2 is of length 2 only, directly this edge. 1 to 3, I need to come here. 1 to 3, I can either take this edge of 8, or there is a better path, that is 2 plus 5 equal to 7. So that's the shortest path between 1 and 3. 1 and 4 also similarly. 1 to 4 I can directly use this edge, that is 5. 2 to 3 I can directly take this edge, that is 5. 2 to 4, I need to come from here to, so either I can take this edge of weight 8, or there is a better path, that is 2 plus 5 via node 1, that is 7. 3 to 4, one path is this 8 plus 2 plus 2, that is 8 plus 2 plus 8, that is 18. There is a better path, that is 5 plus 8, that gives 13. And there is an even better path, that is 5 plus 2 plus 5, this path, that has a length of 12. So these are the shortest path between each pair of vertices, if you are considering that this edge weight doesn't exist. Now as you can see, even the longest shortest path has a length of 12, right? So if I am taking x equal to 13, if I am including that in any of the paths, then the value will be greater than equal to 13, right? But already we have a value less than or equal to 12. So if we take x equal to 13, at least if you are including x, the path will be at least 13. So we have better paths without including x. Then each of these will have a value of less than or equal to 12. So we will never include x equal to 13 edge. So x equal to 13 is will never be the answer. Now let us say x equal to 12. Then this edge will become 12. In that case, if you look at the option, if you look at what I have written here, 5 of these will have a value of less than 12 already. There is one edge 3 to 4 having value of 12. So that equals to the value of edge here. So if you see, if this edge is 12, from 3 to 4 I can either come straight using this edge, that is 12, or I can take this path, that is 5 plus 2 plus 2, that is 12. So anyway, between 3 and 4 there are two shortest paths, and one of those contain x and one of those doesn't contain x. The value is 12, but two shortest paths, in one there is x, in one there is not x. In the question they were asking for which value of x at least one shortest path between some vertices will contain the edge. So there were two shortest paths and there is one path which contains the edge x. So this satisfies the conditions given in the question, that is at least one path contains that edge having a value x. So the largest value of x will be 12 only here in this question. Let G be a complete undirected graph on 4 vertices having 6 edges with weights being 1, 2, 3, 4, 5 and 6. The maximum possible weight that a minimum spanning tree of G can have is dash. So this is a question from data structures regarding minimum spanning trees. Now in the question they have given us a graph G having 4 vertices and 6 edges, meaning that it's a complete graph. If you have 4 vertices and there are 6 edges, meaning it's a complete graph where each edge is connected to every other edge. So a graph looks like this. Now we know the edge weights are 1, 2, 3, 4, 5 and 6. Now the maximum possible weight that this minimum spanning tree of G can have is dash. That's what we need to find out. So these are the edge weights, okay. So let us try to sort these edge weights in ascending order. We are trying to apply Kruskal's algorithm to find out the minimum spanning trees, okay. So we will be sorting the edge weights like this. After that, Kruskal's algorithm will choose the smallest edge from this, that is edge of 1. Now that edge will be added to the minimum spanning tree of the graph unless that edge connects two different vertices which belongs to an already computed minimum spanning tree, okay. You can learn Kruskal's algorithm to learn more about that, what I said down. So anyways, the first edge will always be selected. So let us say edge 1 is selected. Let us say edge 1 is this edge, okay. Now let us see if edge 2 will be selected always. So what I am trying to achieve here is that I am trying to somehow avoid a smaller weight so that a larger weight will be selected, so that the possible weight will be maximized. That's what I am trying to do here. I am trying to avoid some edge when it is sorted in this way. I am trying to avoid some edge so that I can later choose a bigger edge. So let us see if we can try to avoid this edge 2. So edge 2 can be avoided only if that edge connects two nodes which is already there in the current minimum spanning tree. So the current minimum spanning tree is connecting this node and this node. Whatever edge we choose, it will be looking like this only, a minimum spanning tree of connecting two vertices. So if one more edge can be avoided only if it's an edge between two nodes in the same minimum spanning tree. That is, if it's an edge like this only, we can avoid the second edge. But it's a simple graph, so there is no repeated edges between two nodes. The graph looks like this. So whatever node I choose, it will be adding a new node. Either if I choosing this edge or this edge, it will be adding this node to the minimum spanning tree which we computed already. If I am adding this edge, it will create a separate minimum spanning tree and later it will be connected. So whatever edge I choose, it will be selected by the Kruskal's algorithm here. Wherever 2 was, it will be selected by Kruskal's algorithm. So 2 will always be selected as well. Now let us see if we can avoid 3. We can avoid 3. So when we have selected edges 1 and 2, graph will look either like this. We have selected 2 edges, or it will look like this. Okay. Now a third edge can be avoided only if it is between 2 vertices in the same 2 vertices already in the minimum spanning tree computed. So if you take a look at this graph here, if I have edge like this, if edges are 1, 2 and 3 like this, 1 will be selected, 2 will be selected. So these 3 vertices are selected, but 3 won't be selected because 3 is only connecting these 2 vertices which is already there in the minimum spanning tree, right? It will only form a cycle here. So 3 we can avoid in this format, meaning if I am giving edge weights 1 to this edge and 2 to this edge and 3 to this edge, the algorithm will pick this edge first, and it will ignore this edge because it is already connecting the same minimum spanning tree again. So this way I can avoid 3, meaning I can choose a bigger edge later. Now if you take a look here, there are 4 vertices, right? And a tree having 4 vertices will be having 3 edges only. A tree having n vertices will be having n minus 1 edges. So 4 vertices will be having 3 edges. A tree with 4 vertices, meaning we only need to select one more edge. So the maximum we can obtain if we are choosing the edge with 6, but already 1, 2 and 3 is assigned like this. We have connected the graph like this. So whatever other edge we take, these 3 edges are left. All of these 3 edges is connecting this node, meaning the smallest from among these edges will be selected to connect this node to the graph, meaning that 4 will always be selected if we are avoiding 3. So if the graph looks like this, let's say 4, 5, 6, we will first choose 1, then we will select 2, 3 we will ignore, after that we will select 4. So this is the only way in which we can maximize. Either we have to avoid 3 and select 4, or we have to select 1, 2 and 3. There is no other option to construct a minimum spanning tree. So if you are choosing 1, 2 and 4, the total weight will be 7. And 7 is the maximum possible weight of that minimum spanning tree. 7 is the answer. G equals V comma E is an undirected simple graph in which each edge has a distinct weight and E is a particular edge of G. Which of the following statements about the minimum spanning trees MSTs of G is or are true? Then we have 2 statements here. 1. If E is the lightest edge of some cycle in G, then every minimum spanning tree of G includes E. Statement 2. If E is the heaviest edge of some cycle in G, then every minimum spanning tree of G excludes E. And we have been given 4 options. So this is a question coming from minimum spanning trees. Here we have been given 2 statements here and they are asking which of these statements are true. So let's look at the first statement. It states that if E is the lightest edge of some cycle in G, then every minimum spanning tree of G includes E. Now I have drawn a sample graph here. So if you take a look in this cycle, this edge is having weight 10, this edge has a weight 12, this edge has a weight of 11. Now in this cycle, 10 is the lightest edge. But if you take a look at the minimum spanning tree for the graph, there are 1, 2, 3, 4, 5 vertices. We need to select 4 edges. We will be selecting only this edge, this edge, this edge and this edge. These 4 edges which will be having weights 1, 2, 3 and 4, which connects all the 5 vertices. In this graph, we won't be choosing this edge, even though this was the lightest edge in this cycle. So saying that if E is the lightest edge in some cycle in G, then every minimum spanning tree of includes E is false. Now let's take a look at statement 2. If E is the heaviest edge of some cycle in G, then every minimum spanning tree of G excludes E. Now take a look at this cycle here. Okay, let us say this edge E is the heaviest edge in this cycle. Now let us say we construct the minimum spanning tree and that E is included in that minimum spanning tree. Imagine. Okay, so if E is included in the minimum spanning tree, we know that in a minimum spanning tree there won't be any cycles. So at least one edge in the cycle won't be included in that minimum spanning tree. I will repeat again. Let us say this is one cycle. Here E is the heaviest edge here, and we construct a minimum spanning tree. This is not only vertex in the graph. Imagine there are more vertices also in the graph. But this is some cycle where E is the heaviest edge, and we construct the minimum spanning tree. And suppose this edge E is included in that minimum spanning tree. Okay. And if that is the case, if E is included, then there will be at least some edge in this cycle which is not included in that minimum spanning tree, because if all edges are included, then it will be a cycle and it won't be a tree, right? So there is some edge here which won't be included in the minimum spanning tree. Now if I remove this edge from that minimum spanning tree, okay, so what happens when we remove one edge from the minimum spanning tree? That minimum spanning tree will be divided into two parts. If I have a tree like this, okay, and if I remove this edge, this part and this part will be separated, right? Then we need to add some edge in order to connect this minimum spanning tree again to form one tree. Now if I remove this edge from the tree, by adding one of these edges into that tree, we can always make that minimum spanning tree complete. I'll repeat again. If this edge is removed, see, let us say I am removing this edge. Now let us say if this vertex becomes disconnected. Now we know all of these belong to some part of the tree. All of the nodes belong to some part of the tree, but the tree as a whole is now disconnected. There are two trees here. We need to connect it again. Meaning, when I am removing this edge, if this vertex alone is disconnected, then I can always add this edge to make it connected again. Or if this edge alone becomes disconnected, then I can add this edge and connect it again. Now if these two vertices belong to two different trees like this, there are some vertices here and some vertices connected to this vertex, some vertices connected to this vertex, let us say, I can always form a cut somewhere and then choose one edge from this cycle, some other edge other than E from this cycle, and add it to the graph in order to make it connected. Let us take some sample graph to explain it clear. Let us say I have a okay, let us say these four are connected to this vertex. Okay, let us say the graph is like this. This is our cycle here. E is the heaviest edge, imagine. Now let us say this edge was there in the minimum spanning tree. Suppose the minimum spanning tree includes these edges 1, 2, 3, 4, 5, 6, 7 and 8. Let us say these edges were there in the minimum spanning tree. Okay, but if I remove this edge, okay, now this vertex, these four vertex will form one tree, and these 1, 2, 3, 4, 5 vertex will form one tree, and we need some way to connect these two together. So if you take a situation like this, we can always add this edge and make that minimum spanning tree connected again. So this edge will always be less than E. So meaning that this is the final minimum spanning tree. Meaning in whatever cases we select, if we remove this edge E from the minimum spanning tree, we can always add some edge having a weight less than E from this cycle and make that minimum spanning tree connected again. Which means that our initial assumption that E belonged this edge E having the heaviest weight belonged to the minimum spanning tree is wrong. So again saying that if E is the heaviest edge of some cycle in G, then every minimum spanning tree of G excludes E. That statement is true. That's what we have shown here. If E is there in the minimum spanning tree, we can find some other edge belonging to this cycle. By removing E and adding that edge, we can always construct the minimum spanning tree again. So this statement is true. Meaning the right answer is option B, 2 only. Let Q denote a queue containing 16 numbers and S be an empty stack. Head of Q returns the element at the head of the queue without removing it from Q. Similarly, top of S returns the element at the top of S without removing it from S. Consider the algorithm given below, and an algorithm has been given here. They are asking the maximum possible number of iterations of the while loop in the algorithm is dash. So this is a question coming from data structures regarding stacks and queues. We have been given this particular operation which we are performing on a queue Q and a stack S, and they are asking what's the maximum possible number of iterations of this while loop. So let's take a look at this here, this while loop. It's saying while q is not empty, do if s is empty or top of s less than or equal to head of q, then x equal to dq of q. Now dq will remove the first element from the q and that is returned into x and push sx, else x equal to pop of s. Pop of s will pop out one element from the stack and that is enqueued back to q. So this operation we keep on doing until q is not empty, until q becomes empty. While q is not empty, we keep on doing this. So until q becomes empty, we repeat this. So let's see what happens here. So I have written the three options here. One is if the top of stack is greater than top of the queue. So initially stack and queue would be empty and we keep on moving elements here and there. So if the top element of the stack is greater than the top element of the queue, we move the element from the stack to queue. If the top element of the stack is less than or equal to the top element of queue, we move the element from the queue to the stack. We keep on doing this until we meet the exit condition, that is the queue becomes empty. So there is no simple shortcut way to do these kinds of questions. We just need to keep on trying for multiple inputs and then we need to find out what the answer would be. So here for the question it's given that the stack contains 16, the queue contains 16 numbers. So 16 is the last number. What we will do is we will try to do it for smaller numbers. Let us say we start with n equal to 2. We need to solve for n equal to 16, that is 16 elements in the queue. We will solve for smaller n's and try to find out some patterns and then we will finally get to the answer when n is 16. So let us say n is 2. So even before that, one point you need to note is we keep on moving elements from the queue to the stack as long as the top of the stack is less than or equal to top of the queue, which means if the queue has elements in sorted order, let us say 1, 2, 3, like this, 3 elements in the sorted order. So this is the top of the queue, this is the stack, okay. So initially stack is empty, so we will be moving this element here, so 1 will be moved here. Now 1 is removed from the queue. After that we will be removing 2 and putting it to 1. So see here, the top of the stack is less than or equal to top of the queue. Even now the condition is satisfied, so we will remove 2 and put it here. Still the top of the stack is less than or equal to q, the top of the element in q. So we will remove this 3 and put it 1. Now the queue becomes empty and then the exit condition is satisfied. So if the elements in the queue are initially in the sorted order, then if there are n elements in sorted order, then we will iterate the while loop only n times, because each time we will be moving it from the queue to the stack and never we will be moving the element from the stack to the queue. So if there are n elements in sorted order in the queue, the while loop will iterate only n times. But we need to find out the maximum, we need to find out some arrangement of the n numbers which will maximize the number of while loop iterations. Okay, so this property we know. And one more thing, when we are adding to the stack, we will be adding at the top only. But if you are removing some element from the stack and adding it to the queue, we will be adding it at the end of the queue, not the top, since it's a queue, right? Enqueuing will happen at the end of the queue and dequeuing happen on the top of the queue. But for stack, enqueuing and dequeuing both happen from the top. Now, let's come to the question. Let us say n is 2 and let us say it is in descending order, 2 and 1 here, okay? Now, initially we will be moving this element 2, initially stack is empty, so we will be moving the element 2 from the queue to the stack, which I have written here, q meaning queue, s meaning stack. We are moving the element 2 from the queue to the stack. I have denoted like 2 and arrow, meaning that 2 is moved from queue to the stack. Now that is one operation. Now if you look, the top of the stack will have the element 2, right? So top of the stack is greater than top of the queue now. What will happen now is we will remove this element from the stack and we will add it to the queue, meaning, so this was already removed, we will be removing this and adding it back to the queue. But in the queue we won't be adding it at the top, we will be adding it at the end, right? So after 1 we will be adding 2, okay? So that I have denoted here, this 2 I will move back to queue. Similarly, now I will be moving this 1 back to the stack since stack is empty. So this 1 is moved to the stack. Now if you see, the stack has element 1 and the queue has element 2, meaning 1 is less than 2 here, so we'll be moving this element here, so 2 will be removed and put here, so 2 will be moved to the stack. Now both the elements are in the stack, queue is empty. Now we will be done with our operations here. So if n is 2, the answer is 4. For 1 and 2 you can try. For 1 and 2 there are only two combinations, that is 1 2 or 2 1. For 1 2 is in sorted order, that will take only n operations, which I had shown here. When it is 2 1, I showed here, it will take 4 operations, that is 2n operations. So this is the answer for n equal to 2. Let's try to solve for n equal to 3 as well before we start finding patterns. Let us say n for n equal to 3, it is in descending order. Okay. Now initially we will be moving this 3 from the queue to the stack. After that we will see that 2 is at the top of the queue, which is less than what is at the top of the stack. So we will be moving 3 back to the queue. Now the queue will look like this, 2 1 and at the end there will be 3. Okay. Now at the top of the queue we have 2, we will be moving 2 to the stack. After that we will see that what's at the top of the stack is 2, what's at the top of the queue is 1. Now stack has the larger element, so we will be moving the queue, moving 2 from the stack back to the queue. So initially we will be moving 2 from the queue to the stack. After that we will move that 2 back from the stack to the queue. Now the queue will look like this, 1 3 2. After that we will be moving the element 1, which was the top of the queue, to the stack. Now 1 goes to the stack. Now if you see, top of the stack contains element 1. Now when do we move from the stack to the queue? When the stack has some element at the top which is lesser than, which is greater than whatever is at the top of the queue. When the top of the stack has an element which is greater than what is at the top of the queue only, we will be moving it back from the stack to the queue. But now the top of the stack has 1. Okay, and all the elements in the queue are 3 and 2. Both these elements are greater than 1, right? So we will be never moving that element 1 back to the queue, because if we have to move it from the stack to the queue, the condition should be that top of the stack will have an element greater than the top of queue. But right now the top of the stack contains element 1, okay, which is the smallest element in 1 2 and 3. So this condition will never be satisfied, meaning that once the element 1 moves to the stack, it will never be coming back to the queue. Since this condition will never be satisfied for the number 1, which means that once I have done this and I have moved 1 successfully to the stack, this 1 will never move back to the queue. So 1 is stable in the stack now, and that will remain there always. Now let us look at the queue now. The queue will contain elements 3 and 2 now. We will be moving 3 to the stack. After that the top of the stack will be 3, which is greater than 2. So we will be moving 3 back to the queue. After that the queue will look like this, 2 3. After that we will be moving 2 to the stack. Okay, now the stack will contain 2 1 and the queue will contain 3. Again, what's at the top of the stack? That is 2. That is smaller than all the elements in the queue now, meaning this 2 also will never be moved back to the queue, meaning queue 2 is also at a stable position now. Now this will never change in the stack. After that I will be just moving 3 back to the stack. So these are all the operations that will take place when n is 3. Now this takes 9 operations. Now what we have seen is that once the smallest element moves to the stack, it will remain stable in the stack, and after that once the second most smallest element moves to the stack, it will remain stable in the stack and it will never change. After that, once the third most element moves to the stack, it will remain stable at that position, meaning once stack contains the elements in the reverse sorted order, that stack is stable. That is, if we have elements like 1 3 2 4 5, something like this, at the stack it should contain, see, once the smallest element is 1, once 1 moves to the stack, it will remain stable there. After that, once 2 moves to the stack, it will remain stable there. After that 3 moves to the stack, then 4 should come, then 5 should come. Once some arrangement like this appears, once 1 comes here, it will stay there, once 2 comes here, it will stay there, once 3 comes here, it will stay there, meaning in the stack it will be in reverse sorted order like this. And once this order gets satisfied, whatever element is satisfying that order, that will stay stable there only. Now let us take some example where n is 4. Now we know that if n is 4, let us say the numbers are 1, 2, 3 and 4. We know that once 1 moves to the stack, it will be stable there first of all. First we have to move the smallest element to the stack. Now the maximum number of operations we can do in order to move the smallest element to the stack is, the smallest element should initially be at the bottom of the queue, and then for each element we will be moving it to the stack, and then we will be moving it back to the queue. For the second element also we will be moving it to the stack, then we will be moving it back to the queue, like that way. So if there are 4 elements, before the smallest element, the 3 elements we should keep on moving to the stack and back to the queue in order to maximize the number of operations. So, but if one was at the top of the queue, then once we move it to the stack, it will stay there and it will be stable there only. So for 1 to maximize, if there are 4 elements, this 4 I can move twice, this 3 I can move twice, this 2 I can move twice, after that this 1 I will have to move. Meaning for 1, the maximum number of operations I can do switching between the stack and queue is 7, if n is 4. Similarly, after that we have 4, 3 and 2. Similarly, for 2, the maximum number of operations that I can do back and forth is 4 I will move back and forth, 3 I will move back and forth, then 2 I will move once. So for 2, the maximum number of operations that I can do is 5. Each operation will take 1 iteration of the while loop. Similarly, for 3, the maximum number of operations I can do now is only 3 operations. That is 4 I will move once, then I will move 4 back to the queue, after I will move 3. For the last element there is only 1 operation, that is from the queue to the stack. So for n is equal to 4, the number is 16. You can try some other combination and you will see that the number of operations will always be less than or equal to 16. So now we got the pattern here. For n is 2 it is 4, for n is 3 it is 9, for n is 4 it is 16, meaning for whatever n, the maximum number of time we can move the switching back and forth is n square times. Meaning for our question, if the n given was 16, meaning 16 square is the answer to our question, that is 256. Consider the following context-free grammars. G1 such that S gives AS or B, B gives B or BB. G2 such that S gives AA or BB, A gives AA or B or epsilon, B gives BB or epsilon. Here this A and these two B's, this A, this B, this A, this B are the terminals, the rest are the variables. Which one of the following pair of languages is generated by G1 and G2 respectively? And 4 options have been given. So we need to find out the strings generated by the grammars G1 and G2 and then look at the options and say which of these expresses the language correctly, G1 and G2 both. Now this is a question coming from theory of computation section regarding grammars. So let's take a look at the grammar G1 first. We will be looking at the B production here first. Here if you take a look at the B production, what it does is the smallest string I can generate with this is B. B gives this string B directly, or B gives this production B and this B gives this terminal B, or it can give B. Similarly this B can again give small b and capital B, and then finally the variable B gives B. So if you take a look at this, it will show you that this variable B generates strings of the form B plus, that is 0, that is 1 or more B's, string containing one or more B's. Now let's take a look at the S production here. S gives A or B. So S can directly give B, or S can keep on producing AS like that, and at the end one S will give B, which is nothing but writing that S gives, sorry, this was S here. S gives A star, A is terminal, A star 0 or more A's, and then one B variable at the end. But variable B gives B plus, which means S gives A star B plus. That is 0 or more A's followed by 1 or more B's. Now let's take a look at the grammar G2 here. The B production in G2 says B gives BB or epsilon. Now this was similar to this, only difference is that here there is one epsilon, here it was B instead. So if G1 gave B plus, in G2's B will give B star, because see, first I can take epsilon, or I will take B and then this B I can resolve to epsilon, that is a string containing one B, or I can take BB, again B, and then at the end I'll resolve this B to epsilon, that is string of two B's. Similarly, So the variable b will generate strings b star. Now let's take a look at a. A gives a or b or epsilon, which means either I can directly give epsilon, okay, that's fine, or I can directly give the variable b and b will give b star, or I can keep on generating a this production. I can keep on taking this production that will keep on generate a's at the start, and at the end there will be variable a, and at the end that variable a I can resolve it to epsilon or b, okay, meaning if I resolve the variable a at the end to epsilon, it will give me the strings a star, or if I resolve it to b at the end, it will give me the strings a star b is variable here, which we will resolve it later, or I could have directly taken b at the start, which would have given me the variable b only straight, which I can rewrite it as, after resolving b, a star or a star, b was b star or b star. Now a will be giving this a star or a star, b star or b star, okay. And coming to s gives a or b, that is s gives a or b. Now what is a? That is an a at the start, and then a star or a star, b star or b star, which I can rewrite it as a star gives a plus, or a star b star gives a plus b star, or a b star will give a b star only directly, or I could have taken it to b, which will be giving b and b star, that is b plus. So if you take a look here, this is a plus, that is a string of one or more a's, or b plus, that is string of one or more b's, or string of one or more a's and then 0 or more b's, or 1a and then 0 or more b's. This is nothing but one or more a or one or more b's, where a and b, a will appear at the start and then b will appear later. One or more a's and one or more b's. Now we look at the options here. This was a star b plus, that is a power m b power n, where m is greater than or equal to 0 and n is greater than 0. Now if you look at the options, option D captures it correctly. A power m, b power n, m is greater than or equal to 0 and n is greater than 0. Now we look at the second part for G2 as well. A power m, b power n, where m is greater than 0 or n is greater than 0. That is one or more a's or one or more b's, which is what I have written here. So option D is the right answer for this question. Consider the transition diagram of a push down automata given below with input alphabet sigma equal to a comma b and stack alphabet equal to x comma z. Z is the initial stack symbol. Let L denote the language accepted by the push down automata. Which of the below is true? And we have been given 4 options here. So this is a question coming from theory of computation section regarding push down automata. Now let's take a look at the push down automata here and see what language it generates, what strings it generates. So this was the starting state. Okay. So starting state itself is an accepting state. So epsilon is accepted by this push down automata. Now initial stack symbol would be z, that was given in the question. Z is the initial stack symbol. Okay. And it is saying on seeing a and z on the stack, we will be pushing x on top of the z there. After that, on seeing a and x on top of the stack, we will be pushing x on top of the x on the stack, which means that as long as we keep on seeing a, that string will be accepted by this push down automata, since this is an accepting state only, which means on top of epsilon, all strings of a, n number of a, will also be accepted by this language. Okay. Now we have epsilon a, etc. here. Now after seeing some a's, if it sees a b and x on top of the stack, it will be popping that x from the stack and it will be pushing nothing. So it will be just popping that x from the stack and going to this state. After that, when it sees b and keeps on seeing x, it will be keeping on popping the x on top of the stack from the top of the stacks until it sees the initial stack symbol z. At that point, it will just neither push nor pop anything, it will go to an accepting state. So this is nothing but accepting strings of the form a power n, b power n, such that n is greater than or equal to 0. N is greater than 0. There should be at least one a, which will pop at least one x, which will push at least one x to the stack. After that, at least one b will pop that x. After that, if it sees the initial stack symbol, it will go to the accepting state. So that part will be nothing but a power n, b power n, such that n is greater than 0. Now let's take a look at the options. The first one, it says that language is a power n, b power n, such that n is greater than or equal to 0. That is false, because that doesn't cover this part. The language can also generate strings of the form a star, right? So this part alone doesn't cover this. Now option B, a power n, such that n greater than or equal to 0, that is correct. It's covering all of these. Union a power n, b power n, such that n is greater than or equal to 0. Now this part was generating a power n, b power n, n was n greater than 0. But if n is equal to 0, this is nothing but epsilon, that's already covered here. So this is fine. A power n, b power n, such that n is greater than or equal to 0, union this is fine. And is not accepted by any deterministic pushdown automata. Now this part of the statement is false. That's because, see, we only have to do either one of two things. One is, as long as we keep on seeing a, just push it to the stack and keep on accepting all the strings. After we see at least one b, we will be keeping on popping whatever is there in the stack until the stack becomes empty. After it becomes empty, if there is nothing else, we will be accepting it. So this can be easily done by a deterministic pushdown automata. There is nothing non-deterministic about this. So this part of the statement is false. So B is also false. If you look at D, it's the same, except this part. It says that L is equal to a power n, such that n greater than or equal to 0, union a power n, b power n, such that n greater than or equal to 0, and is deterministic context free. Now that is correct. Option D is the right answer. Now if it is deterministic context free, definitely it can be accepted by a Turing machine that halts on every input. So saying that it is not accepted by a Turing machine is false. So option C is also false. D is the right answer for this. Let X be a recursive language and Y be a recursively enumerable but not recursive language. Let W and Z be two languages such that Y complement reduces to W and Z reduces to X complement. Which of the following statements is true? And 4 statements have been given. So this is a question from Theory of Computation section regarding recursive enumerable languages. So in the question we are touching a point called reducibility. So if a language A is reducible to B, it's given with this symbol. If A is reducible to B, then informally we can say that solving A cannot be harder than solving B. Meaning if A is reducible to B, then solving A has to be at least as easy as solving for B. Okay, now based on that we can write down these properties. One is, if B is recursive, which will imply that A cannot be harder than B, right? So A will also be recursive. If we know that A is recursive enumerable, and if A can be reducible to B, then B also has to be recursive enumerable, because if B was recursive, then A has to be recursive also. But we know A is recursive enumerable, which will mean B is recursive enumerable. Similarly, if A is not recursive enumerable, we can write down that B is also not recursive enumerable. Now also we need to take complement of these languages. Here it's given that X is a recursive language, okay, which means X complement will also be recursive. A complement of any recursive language will be recursive as well. Now Y is recursive enumerable language, which means that Y complement will be not recursive enumerable. Now these are important points from Theory of Computation. So if you don't know these, please refer to the video lectures from Theory of Computation section and learn about complements of various languages. Okay. Now based on this much information, we can now solve the question. Here it's given that Y complement reduces to W, which I can write like this, and we know that Y complement is not recursive enumerable. So Y complement is not recursive enumerable and Y complement reduces to W. Then based on this property, we can say that W is not recursive enumerable. Similarly, Z reduces to X complement, and we know that X complement is recursive, written here, which means Z will also be recursive, that is from this point here. So now we know Z will be recursive, W is not recursive enumerable. if you take a look at the options, you will see that option C, W is not recursively enumerable and Z is recursive. Option C is the right answer. The attributes of three arithmetic operators in some programming language are given below. Operators plus, minus, star, precedence high, medium, low, associativities left, right, left, arity, binary, binary, binary. The value of the expression 2 minus 5 plus 1 minus 7 into 3 in this language is dash. So this is a very simple question regarding associativity and precedence. Now they have given the given associativity and precedence of these operators, and they are asking what would be the final value of this expression. So if you take a look at the operators, plus has the highest precedence. So this plus operation will happen first. 5 minus 1, that will be 6. 5 plus 1, that will be 6. Now subtraction has the second highest precedence here. So this expression is 2 minus 6 minus 7 into 3. So we have to calculate 2 minus 6 minus 7. To find out how that will happen, we need to find out the associativity of this operator. Now for minus, it is right associative, meaning if we have 2 minus 6 minus 7, 6 minus 7 will happen first, and after that 2 minus whatever we have. So the bracket will look like this. This minus this will happen first, and then this 2 minus this. Now 6 minus 7 was minus 1. 2 minus minus 1 becomes 3 in total. Now at the end we will be doing 3 into 3, that is 9. So the answer to this question is 9. Consider the following syntax directed translation scheme with non-terminals uppercase SA and terminals lowercase ab. S gives A, print 1, S gives A, print 2, A gives SB, print 3. Using the above syntax directed translation scheme, the output printed by a bottom-up parser for the input AAB is, and 4 options have been given here. So this is a very simple question asking us about syntax directed translation, that's coming from compiler design topic. So we'll draw the parse tree for deriving AAB, and then we'll find out what the output will be. So the parse tree for generating AAB will look like this. S gives A gives SB, and S gives A. So if you look at the parse tree, in a bottom-up parser, first this reduction S gives A will happen. Now when this happens, it will print 2 associated with it. After that, we'll have the string AB, which will reduce to A using this one. A gives SB, reducing to A. When that happens, it will be printing 3 here. After that, we have A, which will combine and produce S according to this rule. So when this happens, it will be printing 1. So in a bottom-up parser, first this part happens, and then this reduction happens, and then this reduction happens. So the output would be 2, 3 and 1 at the end. So the answer is option C. Consider a computer system with 40-bit virtual addressing and page size of 16 kilobytes. If the computer system has a one-level page table per process and each page table entry requires 48 bits, then the size of the per process page table is dash megabytes. So this is a simple question coming from paging topic in operating systems. So in the question, they have given us that the size of a page is 16 kilobyte. And the size of the virtual address is 2 power 40 bits, that is 2 power 40 bytes, assuming that the system is byte addressable, that is equal to 2 power 30 kilobytes. That's the size of the virtual memory. Therefore the number of pages will be equal to 2 power 30 by 16, that's equal to 2 power 26. Now that will be equal to the number of entries in page table. Each page will have one entry in the page table. Now let's try to find the size of the page table. Page table size will be equal to number of entries in page table into size of each entry, that is equal to 2 power 26, which we calculated here, into 48 bits, that's equal to 2 power 26 into 6 byte. 48 bit is 6 bytes, that's equal to 2 power 20 into 2 power 6 into 6 bytes. Now 2 power 6 into 6 is 384, 2 power 20 byte is megabyte. So the final answer is 384 megabyte. They were asking in megabytes, so 384 is the answer. Consider a disk queue with requests for input-output to blocks on cylinders 47, 38, 121, 191, 87, 11, 92, 10. The C-look scheduling algorithm is used. The head is initially at cylinder number 63, moving towards larger cylinder numbers. The cylinders are numbered from 0 to 199. The total head movement in number of cylinders incurred while servicing these requests is dash. This is a very straightforward question coming from disk scheduling algorithms topic in operating systems. Now in the question they have asked us about C-look scheduling algorithms. So if you don't know about various disk scheduling algorithms, please take a look at the video lectures to learn about the various ones. Here in the question they are asking us about C-look. So these are the requests which I have given in sorted order. Initially they are saying that head is a 63. So and moving towards higher cylinder numbers. So what C-look scheduling algorithm would do is it will keep on moving right and it will keep on servicing whichever requests are there in the order. After reaching the rightmost point of the request, now the request end at 191. After 191 it will again move to the leftmost request. That is, it will move to the leftmost part in the cylinder having the smallest request, and from there it will again keep on moving right and keep on servicing the request whatever is unserviced left. So we start from 63, we move to 191. By that time we will cover 87, 92, 121 and 191. From 191 we will move to 10. In this movement nothing will be serviced. After that from 10 to 47 we move, servicing 10, 11, 38 and 47. So total head movements incurred is 63 to 191, 191 to 10 and then 10 to 47. So that total movements are 191 minus 63, that is 128, plus 191 minus 10, that is 181, plus 47 minus 10, that is 37. The total is 346. Consider a computer system with 10 physical page frames. The system is provided with an access sequence A1, A2, etc. up to A20, then again A1, A2, etc. up to A20, where each AI is a distinct virtual page number. The difference in the number of page faults between the last in first out page replacement policy and the optimal page replacement policy is dash. So this is a question coming from operating systems topic regarding page replacement policy. So here they are asking for this particular access sequence, given that we have only 10 physical page frames available for the process, what will be the difference between the number of page faults generated by the last in first out page replacement policy and the optimal page replacement policy. So let's take a look here. First of all, we have 10 physical page frames. The access sequence is 1, 2 up to 20. So we'll keep on adding 1, 2, 3, 4 etc. up to 10, and once we reach 10, all the 10 page frames will be used up. Now all these 10 were initial access, so all of these will create one page fault since this was not already available, right? And it's a first access, so 1 to 10 will anyway create page faults. After that, when it comes to page 11, we don't have space in frame, so we need to swap out 1. And they are saying we are using last in first out strategy, meaning 10 came in last, so we will be removing 10 first and adding 11. So this creates another page fault. After 11, 12 we need to add. Again we will be removing 11 only because that came in last. So 11 will be removed, 12 added. Similarly 13, 14, 15, 16, 17, 18, 19 up to 20 we will keep on adding like this. So finally we will have pages 1 to 9 available and 20 also available. After that what happens is we will be restarting again from A1. So we will be accessing A1 again. Now if you see 1 we already have. So 2 we have, 3 we have, 4 up to 9 we have, right? After that we will be trying to access 10. Now 10 we don't have, we only have 1 to 9 and page 20 available. So 20 will be removed and 10 will be added here, that will cause a page fault. Similarly again 10 will be removed, 11 will be added, 11 will be removed, 12 will be added, etc. Up to 20 will be added, each of which will generate one page fault each. So if you take a look in the first run, 1 to 20 all will create a page fault because it was the first reference. After that 1 to 9 will not create a page fault, but 10 to 20 all will create a page fault. So the total page faults for this algorithm is 20 plus 11, 20 meaning 1 to 20 in the first iteration and 11 in the second iteration, that is for pages numbered 10 to 20. 1 to 9 were already there in memory. So total 31 page faults will be generated using this. Now let's take a look at the optimal page replacement algorithm. For optimal, what happens is 1 to 10 will keep on adding in the page frames available, 10 page frames. After that we are trying to access 11. Now what optimal will do is when we have to remove one page and add a new page, we will be removing the page that will be referenced the last in future references. So we have to remove 1 to 10 and add 11. So when we have to do that, we'll be looking at the future references. So in the future, we'll need to access 1, 2, 3, 4, 5, 6, etc. up to 10 and also more. So among these 10, 10 will be the referenced last in the future. 1 will be referenced first in the future. So since 10 will be referenced last in the future, we'll be removing 10 and adding 11. Similarly, we'll be removing 11 and adding 12, 13, 14, 15, 16 up to 19. We'll be removing and adding 20. So this will work just like the last in first out page replacement policy we did here, creating 20 page faults now. Now we'll have the sequence again, A1 to A20. So 1 to 9 is already there. Okay. Now we need to remove 10. Now we need to remove. Now we have 1 to 9 and 20 in the page frames. Okay. Now we need to remove 20 and add 10. But in last in first out page replacement policy, what we were doing was we were removing this 20 again and adding 10. But in optimal, we won't be removing 20 because this was the second iteration, right? We want to add 10 now, but we can see that in the future 20 is being referenced. So 20 won't be removed. Instead, it will remove any one of 1 to 9 only, since these won't be referenced anymore. So 20 we'll keep here, 1 will remove and add 10. Similarly, any we can remove and add 11, 12, etc. up to 19. After that, 20 we are referencing, but 20 was already there available in the page frames. For last in first out, the last 20 also created a page fault, but in optimal, the last final 20 won't create a page fault. It will already be there in the frames. So the total page faults will be 20 plus 10. 20 is for 1 to 20 and the 10 is for pages 10 to 19. The last 20 will save one page fault by using the optimal algorithm compared to last in first out page replacement policy. So the difference is 31 minus 30, that's equal to 1. Consider the following proposed solution for the critical section problem. There are n processes P0 to Pn-1. In the code, function Pmax returns an integer not smaller than any of its arguments. For all I, Ti is initialized to 0. Now the code for Pi is given here. They are asking which of the following is true about the above solution, and 4 options are given here. So let's take a look at the code for Pi. It says this is the do while loop here. Inside the do while loop it says C of I equal to 1, T of I equal to P max of T0, T1 etc. up to Tn-1 plus 1, C of I equal to 0. For every j not equal to I in 0 to n-1, while C of j, this is a while loop that will stop here, while T of j not equal to 0 and T of j less than or equal to T of I, again another while loop. Then after this critical section, then Ti is initialized to 0, after that remainder section. So this is the code for the critical section given here. Here there are n processes P0 to Pn-1 and they are asking which of these 4 options is true. Now let's go through these options one by one and see which all we can eliminate. First we look at option D, it cannot cause a deadlock. Now initially let us say we have 2 processes P0 and P1. Now T of 0 and T of 1 will be initialized to 0 initially. Okay. Now let us say P0 and P1 both wants to run simultaneously. So both starts. Let's look at P0 now. P0 will assign C0 equal to 1. Okay. T0 equal to P max of T0, T1 etc. up to Tn-1. So this P max function, they have only said that it returns an integer not smaller than any of its arguments. So let us say this P max function returns the maximum of T0 to Tn-1. It's just saying P max returns an integer not smaller than any of its arguments. So we can choose any function that satisfies this condition. One of the function is that it will return the maximum of T0, T1 etc. to Tn-1. So if it is returning maximum, P max will return 0 to n minus. All of these are 0 initially. So P max will return 0 plus 1. So Ti will be 1. Now we are going to assign Ti equal to 1, but let us say before this assignment happens, P1 also calls Pmax and assigns it to T1. See, that can happen without any issues. We don't have any critical section for running this part. So these 2 parts can run simultaneously. So P1 will also run Pmax at the same time. It will, at that time, T0 up to Tn- will also be all zeros. So this will return 0. 0 plus 1 will be 1 and T1 also will be 1. So P0 and P1 both calls Pmax simultaneously. Pmax will return 0 to both P0 and P1. So T0 and T1 both becomes 1 after execution. Okay. Now for every j not in 0 to n minus 1, while C of j, it will be stuck here, but C of j will be 0 for both P0 and P1 because of this condition here. Now look at the second condition, while T of j not equal to 0 and T of j less than or equal to T of I. So for P0, the condition here checks P1 not equal to 0, that is true because P1 is 1, T1 is 1, and T1 less than or equal to T0, that's also true, 1 is less than or equal to 1. So P0 will be stuck. Similarly for P1 also it will look T0 is not equal to 0, that is true, and T0 less than or equal to T1, that's also true, 1 is less than or equal to 1, which means both P0 and P1 will be stuck here. Now that is clearly a deadlock, none of them can proceed further, so it can cause a deadlock. Deadlocks are possible here. So this is false, option D is false. Now look at option C, progress condition is satisfied. Now if there can be deadlock, then definitely there can't be progress, so option C also is false. If progress is satisfied, it will mean that deadlock will never occur. So option C and D we have eliminated. Now there is only options B and A. Now let's take a look at option A. At most one process can be in the critical section at any time. So suppose we have a few processes P0, P1, P2, etc. Now we have already seen the deadlock condition. Now let us say deadlock is not occurring here. So let T value be assigned like this. For P0 let the T value be 1. For P1 let it be 2. For P2 let it be 3, etc. So if processor assign values like this, you will see that in this loop a process I can enter the critical section only when there is no other processes having a T value less than or equal to the T value of the current I. Let us call this T value as timestamp, which means that a process I can enter the critical section only when there is no other process having a non-zero timestamp as well as having a timestamp less than or equal to the current timestamp. So here we saw that if two processes have the same timestamp, then it will cause a deadlock. In that case, no one can enter the critical section. But if all the processes are having unique timestamps like this 1, 2, 3, etc., then at this point, even P2 tries to enter, it will see that P1 has a timestamp 1 that is less than or equal to 3, so P2 can't enter. Similarly, P1 also can't enter because there is another process 1 having timestamp less than or equal to 2. So in this point, only P1 can enter, and after P1 enters, it will make its timestamp equal to 0. After this, from these two processes, P2 can't enter because again it will see that there is a non-zero timestamp 2 which is less than or equal to 3. So P2 can't enter the critical section at this point, but P1 can enter because there is only one other non-zero timestamp, that is 3, which is greater than 2. So after this only P1 can enter. Once P1 enters, this will also be 0, and after that P3 can enter. So this after P3 runs, this will also be 0. Similarly, if there are all the processes have unique timestamps, then only one of the process having the lowest timestamp will enter. If some process had same timestamp, which can occur as I showed earlier, in that case it will cause a deadlock only. So two can't simultaneously enter. So saying that option A, at most one process can be in the critical section at any time, is correct. Now option B, bounded wait condition is satisfied. We'll explain that also here. So if processes had unique timestamps, let us say at some point a process P is assigned some timestamp value of 5. If that's the case, until this process completes, before this process completes execution, whatever other process come will have a timestamp greater than or equal to greater than 5 only. So after one process arrived, there one newer processes arriving can't go into the critical section. I'll repeat again. Suppose one process P arrives and gets some timestamp. Whatever process arrive after P, let us say some process Q arriving after P will have a timestamp greater than or equal to 5 only. A timestamp greater than or equal to 5 only, like 6, 7, etc. Some greater value. So a process Q which arrives after P can't enter before P. So in that case, bounded wait is satisfied if you interpret it that way, but clearly you can see that there is a timestamp as well. In some, there is a deadlock as well. So in some implementation, a bounded wait would mean finite waiting time. But if there is a deadlock occurring, finite waiting time condition is not satisfied. So we can't say that bounded wait condition is satisfied. That also we can't say. That's what is also is false. So A is clearly the right answer here. Consider the following two-phase locking protocol. Suppose a transaction T accesses for read or write operations a certain set of objects O1 up to OK. This is done in the following manner. Step 1. T acquires exclusive locks to O1, O2, etc. up to OK in increasing order of their addresses. Step 2. The required operations are performed. Step 3. All locks are released. The protocol will A. Guarantee serializability and deadlock freedom. B. Guarantee neither serializability nor deadlock freedom. C. Guarantee serializability but not deadlock freedom. D. Guarantee deadlock freedom but not serializability. So this is a question regarding two-phase locking protocols coming from DBMS topic. So if you learn two-phase locking protocol, you will see that this is conservative two-phase locking protocol, and conservative two-phase locking protocol is conflict serializable, which means that this locking protocol is serializable. That is correct. So serializability is guaranteed. Now coming to deadlock freedom. So here it is said that we are accessing exclusive locks to O1, O2, etc. up to OK in increasing order of their addresses. So if some transaction has to access, let us say, 5 objects, it will start acquiring locks to the objects only in the increasing order of their addresses, which means that there can never be circular wait condition. See, when does circular wait condition happen? Let us say T1 needs 1 and 5, T2 needs the same 1 and 5. Let us say T1 got 5 initially and T2 got 1 initially. Now T1 will need 1 which is with T2, and T2 will need 5 which is with T1. That is circular wait. One is waiting on the other, both in a circular manner. But if T1 and T2 are acquiring locks in the increasing order of their addresses, both will try to acquire lock to 1 only first, which means that either T1 or T2 only will get the lock to object 1. Let us say T1 got the lock to object 1. Now T2 will never get the lock to object 1, and T1 can easily get the lock to object 5. T2 will never get the lock to object 5 because it already hasn't got the lock to object 1, and it can only access in the increasing order. So if all transactions are only asking locks in the increasing order of the addresses of the objects, then circular wait condition will never be satisfied. So deadlock freedom is also guaranteed, which means that looking at the option guarantee serializability and deadlock freedom, option A is the right answer here. Consider that B wants to send a message M that is digitally signed to A. Let the pair of private and public keys for A and B be denoted by kx minus and kx plus for x equal to A comma B respectively. Let kx of M represent the operation of encrypting M with a key kx, and h of M represent the message digest. Which one of the following indicates the correct way of sending the message M along with the digital signature to A? 4 options have been given. So this is a very straightforward question coming from computer security regarding digital signatures. So in the question it's given that B wants to send a message M to A after signing it digitally. So what is the correct way of doing it? So if B wants to send a message M to A, what B will do is, first B will send the message M to A straightforward without encrypting it or anything, and then B will take a hash of the message, which is a smaller digest of the message, and then B will encrypt it using B's private key. Why B does that is that when B is signing a message, it should be done by B only. No other should be able to sign saying that B is signing it, which means that B should be encrypting it using B's private key, because no one else will have B's private key, so B is the only one who can encrypt it using private key. Also, once B has signed something, anyone in the world should be able to verify that the signature was actually by B, which means that once B encrypts with B's private key, anyone in the world should be able to decrypt it using B's public key, which B's public key is available to anyone in the world, so anyone can decrypt it and verify that it is B's signature. So the right way of doing it is that B will send the message straight to A. Also, B will take the hash of the message and then sign it, meaning that B will encrypt it using B's private key. This operation can be done by B only. At A's side, A will receive the message. A will decrypt the signed message using B's public key and verify that what A gets at the end is the hash of the message. The hash can be calculated by anyone also. After that, A will verify that the message and the hash is same. If it is same, it means that it was signed by B only. So the right way is message plus encrypting the hash of the message using B's private key, which is option B. Message, hash of the message encrypted with private key of B. The other options are wrong. An IP datagram of size 1000 bytes arrives at a router. The router has to forward this packet on a link whose MTU, maximum transmission unit, is 100 bytes. Assume that the size of the IP header is 20 bytes. The number of fragments that the IP datagram will be divided into for transmission is dash. So this is also a straightforward question from IP fragmentation from computer networks topic. So if you don't know about fragmentation that happens in IP, please refer to the video lectures first to learn about those. So in this question, they have given that the maximum transmission unit of the link is 100 byte, which means that over the link, so initially a packet of size 1000 bytes arrives at the router. Now the router has to forward this packet over a link to some other router, okay. But it is saying that the maximum transmission unit of the link is 100 byte, which means that the maximum size of the IP datagram that can be sent over the link is 100 bytes. So the router will have to divide this IP packet which arrives of size 1000 bytes into smaller packets, smaller IP datagrams, and then after that the router needs to send it over the link, because the link can't support an IP datagram of size 1000 bytes. It can only support an IP datagram of size 100 bytes. So an IP datagram of size 100 bytes will be having an IP header of 20 bytes. That was given in the question. Assume the size of the IP header is 20 bytes. So if the header is 20 bytes, the data part will be 80 bytes. The data part is nothing but the TCP segment. So an IP datagram will have a header of 20 bytes and data of 80 bytes. Meaning in an IP packet, we can at most send a data of 80 bytes only. Now the initial packet had a size of 1000 bytes, which means a header of 20 bytes and a data of 980 bytes. So this data of 980 bytes we need to divide into smaller packets of size 80 only. 80 because the data part can be 80 only. Each IP datagram will have its own header adding 20 bytes. So this 980 we need to divide into packets of size 80, which we can do as 980 by 80 is 12.25. That means 13 packets. So we need to divide this packet of size 1000 into 13 packets. The first 12 will have a data part of 80 plus a header of 20. The last one will have the remaining data part and a header of 20. So the answer is 13 packets. For a host machine that uses the token bucket algorithm for congestion control, the token bucket has a capacity of 1 megabyte and the maximum output rate is 20 megabytes per second. Tokens arrive at a rate to sustain output at a rate of 10 megabytes per second. The token bucket is currently full and the machine needs to send 12 megabytes of data. The minimum time required to transmit is dash seconds. So this is again a straightforward question coming from token bucket section in computer networks. So please refer to the video lectures for token buckets first in order to learn about the algorithm and all the properties of that in order to solve this question easily. So in this question we'll take a look at how it works. So it is said that initially the token bucket is full. Okay, so while the token bucket is full, we can have an output rate of 20 megabytes per second. When we have tokens available in the bucket, we can keep an output rate of 20 megabytes per second until the tokens in the bucket become empty. Now after the tokens are empty, the tokens arrive at a rate of 10 megabytes per second. So tokens arrive into the bucket at a rate of 10 megabytes per second. So initially we had 1 megabyte worth of tokens in the bucket. So that data we can send out at a rate of 20 megabytes per second plus whatever is coming into the bucket also we can send at 20 megabytes per second. But after the bucket becomes empty, tokens arrive at a rate of 10 megabyte per second. So we can output at a rate of 10 megabyte per second only from that time. So which means that till the token bucket is empty, the output rate will be 20 megabytes per second. After the token bucket becomes empty, the output rate will be 10 megabytes per second. So let us assume that let t be the time taken for the bucket to become empty. So if t is the time taken for the bucket to become empty, what is the amount of data that will be sent out from the bucket? So for the time t, it will be sending out at 20 megabytes per second. So the amount of data that will be sent out will be 20t. That will be equal to the amount of data that was already there in the bucket, that was 1 megabyte. Plus also we can send that 1 megabyte out at a rate of 20 megabytes per second for some time t, but in that time t, new tokens will keep on arriving into the token bucket. So that also we can send out at this rate only till that bucket becomes empty. So after a while the bucket will become empty, and after that only the rate will go down to 10 megabytes per second. So for time t, we will be sending out 20 into t amount of data outside, that will be equal to 1 megabyte that was already there in the token bucket plus whatever arrived into the token bucket at that time, that will be 10 into t. Arrival rate is 10 megabytes per second and t is the time at which till which we will be sending at 20 megabytes per second. If you didn't understand this part, please refer to the video lectures, it is explained very clearly there. And once you learn that, you didn't have to go through all this, you could have just applied the standard formula directly here. So we got this expression 10t plus 1 equal to 20t, which means 10t will be equal to 1 and t equal to 1 by 10 or 0.1 seconds. So which means that for 0.1 seconds we will be sending out at a rate of 20 megabytes per second, and after 0.1 seconds we will be sending out at a rate of 10 megabytes per second. So what will be the data sent in 0.1 seconds at 20 megabytes per second rate? That will be 0.1 into 20, that is 2 megabyte. So for the first 0.1 second we will be sending out 2 megabytes. We had a total of 12 megabytes of data to send. So the remaining data is 10 megabytes. After this 0.1 second the bucket will be empty. So we can only output at the input rate only. The input rate was 10 megabytes per second. So the rest of the 10 megabytes we will be sending at 10 megabytes per second rate, that is 10 by 10 equal to 1 second. So in 1 second the entire data will be sent out after this 0.1 second. So the total time taken is 1 second plus 0.1 second, that is a total time of 1.1 second. That's the answer to this question. A sender uses the stop and wait ARQ protocol for reliable transmission of frames. Frames are of size 1000 bytes and the transmission rate at the sender is 80 kbps. 1 kbps equal to 1000 bits per second. Size of an acknowledgement is 100 bytes and the transmission rate at the receiver is 8 kbps. The one-way propagation delay is 100 milliseconds. Assuming no frame is lost, the sender throughput is dash bytes per second. So this is a question regarding stop and wait protocol from computer networks. Here we just need to find out what the throughput would be at the sender side. So in the question they have given that the sender bandwidth and the receiver bandwidth are different. Sender has a higher bandwidth of 80 kbps, receiver has a lower bandwidth of 8 kbps. The propagation delay is also given. So this is how stop and wait protocol looks. If this is a sender and this is a receiver, for sending one packet, it will be sending one packet first and then wait for its acknowledgement and then repeat the same thing again. It will be waiting for acknowledgement for each and every packet. So for the first packet, it will have a transmission delay at the sender for sending the packet, and then it will have a propagation delay, that's the time taken for the packet to reach from the sender to the receiver. After that, the receiver will process it. There is nothing given in the question about processing delays or anything, so we will assume it is 0. After that, the receiver will transmit the acknowledgement back, so it will have another transmission delay for the acknowledgement, and then it will be, the acknowledgement also needs to propagate back to the sender, so that will also add a propagation delay. So the total delays would be t transmission at the sender plus t propagation plus t transmission of acknowledgement plus t propagation for the acknowledgement, and the efficiency will be only this part out of the total. This is the total time taken and this is the time taken doing useful work, that is sending the packet. So efficiency would be t transmission at the sender divided by t transmission plus t propagation plus t transmission of acknowledgement plus t propagation. Now let us calculate all of these values. In the question it is given that t propagation is 0.1 seconds. It's given here propagation delay is 100 milliseconds, that is 0.1 seconds. So this and this is the same only, that is 0.1 second each. Now t transmission at the sender is equal to L by B, where L is the packet size and B is the bandwidth. Then the packet size is, it's given that frames are of size 1000 bytes, that is 1000 into 8 bits divided by The bandwidth is 80 kbps, that is 80 into 10 raised to 3 bits per second. It's given in the question only. That will be equal to 0.1 second. So T transmission at the center will be 0.1 second. Now we'll find out the T transmission for the acknowledgement. That is again L by B, where the packet size of the acknowledgement is only 100 bytes now. That is 100 into 8 bits divided by, at the sender, at the receiver, the transmission rate is a lower one, that is 8 kbps. So the receiver can only transmit at this rate. That will mean L by B would be 100 into 8 bits divided by 8 into 10 raised to 3 bits per second, since receiver had a lower transmission rate. That will be again 0.1 seconds. So all of these delays are 0.1 seconds. Now we can calculate the efficiency, that's equal to T transmission divided by Tt plus Tp plus T transmission of acknowledgement plus Tp, that is 0.1 divided by 0.1 plus 0.1 plus 0.1 plus 0.1, that is 0.1 divided by 0.4, or 25%. Now we will find out the throughput. Sender throughput will be same as, here we have found out that the efficiency is 25% only. So sender throughput would be 25% of the sender's bandwidth. That is 1 by 4 into the sender's bandwidth was 80 kilobits per second, or 10 kilobytes per second. That is 10 into 10 raised to 3 bytes per second. That is 2500 bytes per second. The question they were asking for bytes per second. So the answer is 2500.